Welcome to this Master Multithreading and Asynchronous Programming in C# and .NET 8. Learning multithreading and asynchronous programming is crucial for developing high-performance, responsive, and scalable applications. This comprehensive course is designed to equip you with the skills and knowledge needed to harness the full power of multithreading and asynchronous programming in C# and .NET. Whether you are a seasoned developer looking to deepen your knowledge and expertise, or a newcomer eager to learn, this course has something for everyone. Let's take a look at the curriculum of this course. We're going to start with learning the intricacies of CPU thread and thread schedulers, basic syntax to start a thread, and then the reasonings why we even do multithreading. After that, we're going to learn about thread synchronizations and thread safeties, starting with exclusive locks, then with Mutex, reader and writer lock, semaphores, AutoResetEvent, and as you can see in every single section, we have assignment for you to practice what you have learned. We also cover thread affinity and thread safety, nested locks and deadlock. And then we're going to cover some miscellaneous things regarding multithreading. We're going to talk about debugging programs with multiple threads, states of thread, returning results, canceling a thread, thread pull, exception handling in threads. After that, we're going to move on to task-based asynchronous programming. We're going to talk about multithreading versus asynchronous programming. What are the differences? Again, we're going to start with basic syntax. We're going to have assignments again, and we're going to talk about everything that is related to tasks. For example, wait and wait all, result, continuations, when no, when any, continuation chain and unwrap, exception handling, task synchronizations, and task cancellations. You can see that we not only cover the basics, but also dig really deep into each one of the concepts. And also, almost in every lecture, we have source code attached to each one of the lessons. After that, we're going to move on to async and await. Async and await are the keywords that allow you to write asynchronous programs as if you're writing synchronous programs. You not only know how to use it, and also you know the reasoning behind it, and also you know how it works under the hood. We're going to also talk about exception handlings as well as synchronization context for await. After that, we're going to talk about TPL. The first thing we're going to cover is the parallel loops. Again, we're just going to start with basic syntax, and then we're going to dig deeper into each one of them. Stop, break, parallel loop result, cancellation, thread local storage, performance considerations. After that, we'll come to the second part of TPL, which is parallel link. So with parallel link, you can use link, but at the same time, you add parallelism to your program. Last but not least, we're going to learn about concurrent collections. Especially, we're going to learn about how to use blocking collections to add producer and consumer scenario functionalities to our concurrent data structures. As you have seen, this is not only a theoretical course, but also has a lot of assignment. For example, you're going to learn about how to use multithreading and parallelism to create web server simulations. You're going to learn about using thread synchronizations to create airplane seats booking system. And then we have two-way signaling for producer-consumer scenario. And also we have assignments for returning results from tasks. All of these practices will help you to hammer what you learned into your mind. Feel free to watch the free lessons and go over the landing page. I hope to see you in the course. In this video, let's talk about some basic concepts, including CPU, application, thread, and thread scheduler, so that we can have a basic, solid foundation in order to understand multithreading and asynchronous programming and be able to create multithreading programs and or asynchronous programs. So for any modern computer, we will have to have a CPU, which is the central control unit that process all the applications. Without the CPU, none of the application will be able to run, so the computer wouldn't exist. So let's find an icon of CPU. Okay, so we have a CPU here. For the developer or any user, one of the most important things is the application. That's the whole purpose of having a computer. So let's imagine this rectangle represents an application. And when you have the CPU and then have the application loaded into the memory of the computer, then when the application wants to run, the application have to be processed by the CPU. However, the CPU can only process a thread. So the thread is the basic unit that can run within a CPU, not the application. So therefore, one application has at least one thread. It's impossible that application doesn't have a thread. Without a thread, application wouldn't even exist. It wouldn't perform its task. So let's use a circle to represent a thread within the application. And let's imagine there's only one thread in an application. That's the normal applications. Normal application only have one thread, which usually we call the main thread, or we call it a primary thread. All right, so we have application and we have this main thread. And when the application is loaded into the memory of the computer and wants to run, then the thread has to be assigned to the CPU, and the CPU will process the application. So who is responsible for assigning the thread to the application? And that's something we call the thread scheduler. Now let's use another rectangle to represent the thread scheduler, and I'm going to just call it thread scheduler here. The thread scheduler is this middle person that look at the available applications and then assign this thread in the CPU so that the CPU can take care of the thread. Remember the key concept here. To the CPU, application doesn't exist. To the CPU, only thread exists. Thread is the basic unit that a CPU can process. So the thread scheduler here is responsible to assign a thread to the CPU. Now, it's possible that we have multiple applications. In fact, that's most of the case. You have multiple applications running within the computer. So when that is the case, we use multiple rectangles to represent the scenario. Rectangle represents application, and remember that we have to have a thread inside the application in order for the application to run. So when that's the case, the thread scheduler will have to decide which one of the threads can be assigned to the CPU to run. Not all of the threads can be assigned to the CPU at the same time. Imagine there's only a single core CPU, so at any given moment there's only one thread can be allocated to the CPU for the CPU to process. The scheduler's responsibility is to determine who needs to be assigned to the CPU. The scheduler makes the decision based on many different factors. For example, some of the applications is more mission critical than other applications. So therefore, their thread has higher priorities. And another factor could be that, let's say this is a high priority thread, therefore it is assigned to the CPU, but it's been using the CPU for a long time and the other threads are being starved. So in that case, thread scheduler will have to remove this thread from the CPU and start giving other threads some opportunities to be processed in the CPU. So the task scheduler essentially is assigning the thread, in this case, based on time slicing, which means that each thread has a period of time which we call time slice. And during that period of time, the thread will be assigned to the CPU in order to run. So this is the basic algorithms that a thread scheduler uses in order to process different threads within different applications. Now, the thread scheduler is not something that a developer is able to influence other than assigning some priorities to your own thread. The thread scheduler is a part of the operating system. It's out of our developer control. So you have to be aware of that. Now we have multiple applications and we have one thread in each application. This is not a multi-threading scenario. This is a multiple application scenario. When we talk about multi-threading scenario, we're referring to that the possibility of having multiple threads within one application. Let's say the first application utilizes 3 different threads. Therefore, we call the first application is a multi-threading program or multi-threading application. But to the scheduler, there's total 5 different threads. So 1, 2, 3, 4, 5. 5 different threads in the entire operating system. It doesn't really matter whether the threads belong to this application or not. To the thread scheduler, the only thing it sees are the different threads. So whether there's only one thread or there's 1,000 threads, whether those 1,000 threads belongs to one application or belong to many different applications, it doesn't really matter. Thread scheduler is just doing its work. based on its own algorithms and assign those threads to the CPU to be processed. So each one of those threads will have its turn to go onto the CPU. And of course, you will have scenarios where you have multiple cores of CPU, not just single core. Then here we can use different icons of the CPU to represent the different cores. And it's exactly the same thing. The thread scheduler, which is part of the operating system, will be dealing with assigning different threads to different cores of the CPU. But it's only that this time the thread scheduler will be able to assign one thread per core. But as for how it is done, it is entirely up to the thread scheduler, and we don't need to worry about that. We just need to know that there is the thread scheduler taking care of the threads within our applications. And when there are multiple threads within one application, we're going to call this a multi-threading scenario. For this application, this is a multi-threading program, whereas this is just a regular single threading application. This one is also a regular single thread application. Okay, those are the main basic concepts we need to know before we start programming multi-threading programs. If you have any questions, please let me know. If not, I will see you in the next video. In this video, let's talk about the basic syntax of writing multi-threading program. So let's go into Visual Studio. The Visual Studio I'm having is Visual Studio 2022, and .NET framework that means I have is .NET 8. So let's create a new application, or let's say a new project, and we're going to select the console application, language is C#, and click on next button. And we're going to call this basic syntax. Click on next, framework.NET 8, and click on the create button. The whole purpose of creating any application is to perform a task. In this very, very simple application, there's only one task this program completes, which is to output the words hello world console. And to perform any tasks, usually we use a function or method. In this case, we didn't write any custom functions or custom method. We're using console.write, which is a method that comes from the .NET framework. So let's create a method ourselves in order to perform a task. And I'm going to call this method write thread ID. So it's a very simple task that all it does is to output the current thread ID. I'm going to write it to a line on the console. And in order to output the thread ID, we're going to use the thread.currentThread.manageID. We don't need to add one to it. So this is thread ID. We need to remove one of the parentheses. And now we have a method here. This method performs a very simple task. Of course, in your real world scenario, you have way complicated tasks to perform other than just output the manage ID of the thread. But in this case, it's suffice to illustrate the concept. So we have a method here that performs a task. And when we want to actually perform the task, we want to invoke this method. We invoke it this way. And if we run it, well, actually, let's also do a console line so that we don't just directly exit the program. Okay, let's run the application now. And now you see we have hello world, which is the first task that is performed. I forgot to remove that. And then we have this number 1 that's written out. So this is the ID of the main thread of this application. Well, let's remove this before we forget. Okay, so we have this task that is performed by the main thread, which is why the thread ID is number 1. So in this course, we're talking about multi-threading, right? So in order to start another thread, we're going to use the thread class. So what we are going to do is we're going to say thread dot, let's say we call it thread 1, and then we're going to just create a new thread. And then within the constructor here, you can see that we have different signatures, and all of them takes at least a delegate. So if you read this, start is a delegate that represents the methods to be invoked when the thread begins executing, which means that we are assigning a task to the thread. a thread wouldn't run without doing anything. Right? There's a reason why a thread runs, because it needs to perform a task. So we assign a C# delegate, which is basically a name of the function or the name of the method. In this case, we only have one, which is the read thread ID. So we are going to say that we're going to start a new thread, and all this thread does is to write a thread ID. Again, it's not realistic, but it suffices the purpose of demonstrating the basic syntax of starting a thread. Okay, so starting a thread, you declare the thread, you assign a task to the thread, and then now you're going to say thread 1.start. So this is where you actually kick off the processing of this task in this new thread. Okay, so now let's comment out this read thread. So we're not going to actually invoke this within the main thread. We are only going to invoke it within a separate thread. And now let's see what is the thread ID. Let's run the application. Now you can see that the thread ID is number 7. So this is the same method that was called by the main thread, but now it's outputting number 7 instead of number 1. So that means this thread ID that is written here, which is the current thread, is the new thread instead of the main thread. So what if I am running this thread ID from the main thread and from a separate thread at the same time? So let's give it a try. Now you can see that the main thread still outputs number 1, and then a separate thread. There are different threads, whether this thread ID is 8 or 7, or 28 or 108, it doesn't really matter. It's assigned by the operating system. But this example shows us the basic syntax starting a thread. You declare a thread class, assign a task to the thread, and then you start this thread. Now let's perform a slightly more realistic task. Let's say that instead of writing this ID out just once, we want to write the ID out for 100 times. So we are going to create a loop, and it's going to loop from 0 to 99. It doesn't really matter whether it's from 1 to 100 or from 0 to 99. The point is that we're writing out the same stuff 100 times. Okay, and again, let's comment out this. And now let's start another thread. So don't worry about the main thread. Let's start another thread. And how do we do it? Remember, create a new thread. Let's call it thread 2. And then assign a task to it, which is the same task. We're going to write the thread ID. And then we're going to say thread number 2, start. And when this line runs and this line runs, that means we have 2 threads that runs at the same time. And it's up to the thread scheduler to determine who's going to take which core of the CPU, or are they going to take turns? We are going to find out. Let's run the application. Okay, so in this case, you can see that thread number 8 finished, and then thread number 7 started. But it may not be this case all the time, because this time the thread scheduler is prioritizing one of the threads. But sometimes it may not be the case. Let's run it again. And this time it's different. You can see, so I scroll all the way to the top, number 7 at the top, and then switch to number 8. And now if we scroll down, now we switch to number 7 again, and then it finishes. Okay, so last time it was number 8 for 100 times, followed by number 7 for 100 times. This time it started with number 7, but it didn't finish its 100 times turn. Now it's number 8, and then followed by number 7 to complete. And we run it again, you will see another different results. Scroll up, and this time you can see it started with number 8 and finish 100 times. And then number 7. So this is the same as the first time. So the reason why it's repeating this pattern is because 100 is too fast. Right? For CPU, 100 loops is not much. So in order to slow it down, we can say thread.sleep. So sleep 1000 means 1000 milliseconds. That's 1 second. So that's too long for us. So we don't want to wait for that long. Let's say each iteration, we're going to pause for 50 milliseconds. Then when we run it, we'll see something more interesting. Because if we slow it down, then the thread scheduler will have to work harder to pull the threads in and out of the CPU. So let's run the application again. Now you can see something more interesting, and it's slower. Of course, it's slower. Okay, finally I finished writing, and you can see that 7, 8, 7, 8, they are alternating, but it's not exactly alternating. Here you can see that thread number 7 takes the CPU twice, right? And then followed by number 8. Well, I shouldn't say take the CPU twice, but it took a little bit longer time slice, so it has enough time to write twice. Whereas here, it's just 7, and then 8, and 7, and then 8. And here, number 8 took longer time slice and be able to write twice. So we scroll down. It looks like the longest is just twice. So from this example, you have seen the thread scheduler working. And don't forget, the main thread is also thread. So if we invoke the thread ID here, that means we have total 3 threads running in parallel. And if we run this again, we're going to see something completely different. We're going to see number 1 is being written how many times? 100 times. And then followed by 10, 11 alternating. Why is that? Because thread ID here is in the main thread. It is blocking. So this has to be completed before these 2 threads can start. Right? That's why you see number 1 being written by 100 times, and then these threads starts. When these threads starts, these threads are not blocking. Okay? So this is the nature of using threads. Threads are not locking. So if we move these 4 lines of code above the main thread, then things will be different. Now you can see that we have the 3 different threads alternating. We have 7, 8, 1, 7, 1, 8, 7. There's no particular pattern in this. Sometimes it's taking longer time slice. Here, the main thread, be able to write it twice. From this example, you are able to see that the thread scheduler is working to assign different threads within the application into the CPU. And again, the thread scheduler is part of the operating system. Whether it's going to favor this one, or the main thread, we don't know. In order to influence it, we have some ways. For example, we can use the priority. Now, before the thread starts, move this line downwards, okay? And then move this line up. So here, if we say that thread number 1 and its priority is the highest. Well, first of all, let's take a look at what priority we have here. We have above normal, below normal, highest, lowest, and normal. So 5 different levels. If we say thread 1 is the highest and thread 2, let's say thread 2 is the lowest. And the main thread, how do we let it know? So we're going to say thread.current thread. So this is the main thread dot priority. Let's say this one is normal. And let's run the application and remove the thread.sleep because it's going to affect the algorithm of the thread scheduler. So let's comment it out for now and let's run the application. Now you can see number 7 starts first because number 7 is thread number 1. Oh, sorry, I need to scroll up. It's not number 7, it's number 8. Number 8 is thread 1. So number 8 finishes and then number 1. So this is the main thread and then followed by number 7. So number 7 is the lowest. Thread number 2 is number 7. Thread number 1 is number 8. And the main thread is number 1. Right, so you can see that the priority actually influences the order. Now, like I mentioned in the previous video, that the thread scheduler's algorithm has many factors. The priority is just one of them. The time slicing is another one. So even though you have the priorities assigned like this, each time the work takes too long time, let's say that we have this each time it takes 50 milliseconds here. Now, the result wouldn't be the same. So let's run the application to see what happens. Okay, so we have this running and it's still running. Let's wait for it to finish. Scroll all the way up. And you can see that this is very similar to what we have seen before. Each thread, we have 3 different threads taking turns and there's no particular pattern. Why is that? Why this is the highest, this is lowest, and this is normal? And it seems that they're not actually affecting the sequence. Well, it's really just because the task itself, each time it performs it, it takes just too long time to finish. So the thread scheduler will have to kick it out of the CPU. What the priority of the thread is, it doesn't really matter. So even you can assign the heights to your own thread, you're not going to have the turn because you're too slow. Before we finish this video, I also want to show you that a thread can have a name. So we have thread.name, and you can call it thread1. You can give thread2 a name, and then we can have the main thread, which is thread.current.name, and we can call it the main thread. So now instead of writing out the ID, let's just write current thread's name. So this would be more meaningful at least. So let's write. And you can see that they're alternating because the task itself to perform in this thread is just taking too long time. So we have the names being written out like. All right, so this is the basic syntax of kicking off a thread. You declare a thread, assign it a task, and then just call start. Then it will start the thread. And it will not be blocking. That's the nature of a thread. Whereas if you perform the task without running in a separate thread, you are going to block the current thread. In this case, the current thread is the main thread. That's why this line will not execute before this task is finished. And that's everything I want to cover in this video. If you have any questions, please let me know. If not, I will see you in the next one. In this video, let's talk about why do we need to start a new thread. And one of the first reasons is to solve divide and conquer type of problems. So we have demonstrated how to start a thread, the basic syntax of that. But the task that we want the thread to complete is just to write the thread name or the thread ID for 100 times. That's a silly task. So let's look at some more realistic type of problems that can be solved by use multiple threads. And one of that is called divide and conquer. So what that means is that you have a huge task. So again, let's use this rectangle to represent a task. And I intentionally made the rectangle bigger because I wanted to represent a big fat task. When we look carefully about this task, it appears that we can actually divide this task into different chunks or different sections so that we can let multiple people working on this task. If we are talking about a real life task, if we divide this task into, let's say we divide it into 2 different tasks, then we can find 2 different people to work on that in parallel. So we can have person 1 working on the left chunk and person 2 working on the right one. In real life, we have many type of scenarios like this. For example, cooking. Let's say we're cooking 4 different dishes for dinner. Mom cook on 2 and dad cook on the other 2. That way, instead of taking 1 hour, maybe it's only taking half an hour to finish the cooking process. And then we have the dinner ready. So this type of problem is called divide and conquer. And let's jump into Visual Studio and see whether we can create a scenario where we can simulate this type of problems. So let's close this application that we created previously and create a new project. Still console application, and let's call this divide and conquer and click on the create button. Now, what we are trying to do is that we're going to have an array of integers. So let's say that we have 10 integers. Well, it's more realistic to have 1,000 or 1,000,000, but let's just, for example, we have 10 integers and we want to summarize them. It's a very simple task. You can just use for loop to complete it. So if we were to use single thread to complete the job, becomes very, very straightforward. So we can have a sum and we initialize it to 0. And then we're going to do a for each loop. So we're going to say var number in array. And then as we're looping through the array, we're going to add this to the summary. And then at the end, we are going to output it. And we're going to say the sum is sum. So this is going to give us the result pretty quickly because the array is only 10 elements long. All right, so it says the sum is 55. Now, how do we know how long this takes? So let's get a timestamp. Start time equals datetime now. And then at the end, we're going to get the end time equals datetime now. And here we're going to add another one. We're going to say red line. And we're going to say the time takes is, we're going to get a time span. So I'm going to say time span equals end time minus start time. And then over here, we're going to say time span dot total milliseconds. We can use total milliseconds. If that's not accurate enough, we can use nanoseconds. So let's try milliseconds for now. And at the end, add this read line so the program doesn't exit. Before we actually test it, let's add a thread.sleep here. So thread.sleep, I want it to sleep for maybe 100 milliseconds per each iteration. So this is to simulate a longer calculation. Right? Because we only have 10 elements in the array, it's not long enough for simulating a CPU intensive calculation scenario. That's why I'm using the thread.sleep to simulate that. If we do it this way and then we give it a try, we'll see how long it's going to take to summarize this. So let's give it a try. All right, so the result is 55 and the time it takes is about slightly higher than 1000 milliseconds, which is 1 second. But if we look carefully about this problem that we are resolving, this is very similar to the kitchen problem. Right? So we're cooking dishes and it can be actually split for multiple cooks. Here we're calculating multiple elements in the array, but we don't have to just use one thread. We can use 2 threads, 3 threads. For example, if we're using 2 threads, the first thread calculates the first 5 and the second thread calculates the second 5. And then at the end, we can add the result together to get the total summary. So that way, we're going to shorten the calculation time for sure. So let's give it a try. We can delete this for each, and then we can use threads, multiple threads to solve the problem. Let's say we're going to use 4 different threads. Okay, so we're going to have 4 different summaries, 3 and summary 4. Okay, we're going to divide this task into 4 different chunks. And then we're going to work on that separately. So over here, we're going to say number of threads, and I'm just say 4. And then the segment length, we need to calculate that. Right? So I'm going to say array.length divided by number of threads. And now we're going to have an array of threads because we have 4 different threads. So here, because I have this number of threads, so I'm going to use the number of threads. So num of threads, this creates 4 different threads. And then I'm going to assign a task to each thread. Okay, so thread number 1, which is thread 0, this one equals to new thread. And what it's going to do is to summarize the section. So before we proceed, we need to create a task for the thread to do. So each one of these 4 different threads work on the same thing. Basically, they just summarize the section that they are assigned. So I'm going to create a function. I'm going to call it sum segment. And it has a start index and an end index. And this one has a segment sum, initialize it to 0, and then we're going to loop from the start to the end. And here we're going to say segment sum equals array. Well, this has to be defined first. So we're going to move this to the top. Then here we're going to say array I. So this helps us to calculate the sum of the segment. And once it is done, I'm going to return the segment sum. Now that I have the task, I can assign the task to my thread. So the first thread, which is thread 0, I'm going to say new thread, and then I'm going to use a lambda expression, and I'm going to say sum1 equals sum segment, and that's from 0 to segment length. So here is not thread, but threads. And we're going to do similar thing for the other 4 different threads. Here for the first one, the second one, sum number 2 equals from segment length to 2 segment length. And now sum number 3 for thread number 3 is from segment length times 2, 3 times segment length. Well, probably it would look better if I just put this at the beginning. And then last one is going to be for thread, this is number 2, and this is 3, but sum number 4. And this is going to be starting from 3 times segment length to array length. Okay, so we divided the array into 4 different chunks. But if we change this number, it will be able to divide it accordingly. Now, we are going to start all of the threads. And for that, we're going to loop through the threads array. And we are going to say thread.start. That starts all of the threads. Now remember, this is threading, right? Multiple threading, when we use thread, it starts asynchronously, which means that it's not blocking. And that means that this is going to run through pretty quickly, and you're going to have the end time very, very close to the start time if we do it this way. To get the actual time, we will need to wait over here. We need to intentionally block. To do that, we're going to do for each again, and then I'm going to say thread.join. So when we say thread.join, you can see that blocks the calling thread until the thread represented by this instance terminates. But because we're going through all of the thread, so that means that this line will not run until all of the 4 different threads finishes. And then at the end, we're going to say the sum is sum1 plus sum2 plus sum3. What is the problem here? It says use unassigned. So here, I just need to assign 0 to each one of it. Before I actually try it, don't forget to add a thread sleep here. So thread.sleep for 100 milliseconds. So this is the same as a single thread scenario. And now let's try it again to see how long it takes this time. Okay, so it takes 400 milliseconds. This is way shorter than 1000 milliseconds, which is a single thread scenario. In this case, it's not really a good example to use because we have only 10 elements in the array. Spinning up 4 different threads just for 10 elements is a waste of time. But for demonstration purpose, I added a 100 milliseconds delay in each iteration to simulate a long-running CPU-intensive calculation. So you can see the difference. But in real-life scenarios, you might have thousands of elements in an array, and spinning up multiple threads like this is going to definitely cut down the calculation time. So with this example, you notice that with the divide and conquer type of problems, using multiple threads is very good for improving the performance. And that is the second reason for using multiple threading programming. That's everything I want to cover in this video. If you have any questions, please let me know. If not, I will see you in the next one. The second reason why we want to start a new thread is to offload a long-running task to be handled by a different thread. And when we talk about this type of task, we're referring to the main thread. So that means that we are referring to a regular single thread application. And for a single thread application, everything runs as one task after another, like in a sequence. So for example, if I just use this to represent a task, and then next one is the next task, next one is the next task. So this is a sequential task performing thread. So when one thread is performing all of these tasks one by one, and for example, that the third task is a pretty big task. Let's say this one is pretty big, so I'm making it big and fat. And for a big and fat task, when we use one thread, it still means that the application will have to perform this task and then go on to the next one, and then the next one. So this means that when we have a big and fat task, this is blocking the thread to perform its task. And this thread is happen to be the main thread, which is very critical, especially this application has a UI. right? So it has a user interface, so the user is waiting for the task to be completed. And while the user is waiting, the whole application appears to be frozen. So that's not a good user experience. And that's where we talk about offloading this to a different thread, so that the rest of the task can be immediately performed after this one is started, right? Because this one is started in a different thread, therefore the next task will immediately be performed. And then when this is completed, the result of this task will be handled accordingly. So this is where we use the word offload. And this is where we refer to instead of we say multi-threading, we say asynchronous programming. But we'll talk about that later. Anyway, whether it's asynchronous programming or multi-threading programming is more or less the same thing. We're using multiple threads. In this case, it's a main thread and then a second thread, right? And we call it the worker thread to complete this task. Okay, let's jump into Visual Studio and see some examples. Let's create a new project. And this time, let's create a Windows Form application. If you don't see the Windows Form application in your Visual Studio, you will need to open up Visual Studio Installer. Let's take a look. So Visual Studio Installer, and once it's open, you select your version. I'm currently using this Visual Studio Community 2022. I'm clicking on Modify, and then make sure you select this .NET Desktop Development. Check this and then click on Install. And then you will see, so after installing, you will see Windows Form app appear here. So I'm just using this as an example. So click on Next, and let's name this Offloading Tasks. And then let's click on the Create button. All right, so we have this Form 1. So what I want to do is I want to put two buttons on the form. So let's go to View, and let's click on Toolbox. And let's open up the common controls, and we have button here. So let's drag one button here and another button here. So we can align them up so that it looks slightly better. Maybe pull this down to the middle, and then go to Properties, and we see the text here, button 1. So maybe we'll change this to message 1, and then change this one to message 2. So what I'm intending to do is when I click on the button, it will just display a message, okay? But I'm going to simulate a long running task. So let's double click on this, and then it would automatically generate an event handler, which is a click event handler for the button, which means that everything that I code within this event handler will be executed when I click on the button. Again, task is that we are going to display a message on the form. So coming back to the form, where do we want to display it? Let's drag a label here, and we're just going to display the message on this label. And let's right click on it and then go to Property and name of the label, which is label 1. So we can call it LBL message. So label message, and this is where we're going to display the message. So let's go to the event handler of button number 1. And what we want to do is when we click on button number 1, we want to display the message in the label. So we're going to say LBL message.txt is whatever the message is. And for this example, I'm going to say first message. And then in button number 2, when I click on the message button, I'm going to do the same thing, but with a different message. But this is going to be really, really quick. So in order to simulate a long running task, I'm going to use thread.sleep. So we have used this before. This just means that we're going to hold down to the thread and make the thread pause for 1000 milliseconds, which is 1 second. Okay, so that's probably not long enough. Maybe let's make it 2 seconds. And then for this one, let's make it 3. All right, so if we run this and see what's going to happen, first of all, I'm going to see the form pop up, hopefully. All right, we see the form pop up. And if I click on message number 1, I wait for 2 seconds. Text first message is displayed right here. And if I click on message number 2, I wait for 3 seconds. The second message is also displayed. Now I click on message number 1 again, and then come back, click on message number 2 before 1 is displayed. Okay, let's try again. So let's display message number 2 first. Okay, so it's displayed. And then when I click on message number 1, before it's displayed, I click on message number 2. And let's see what happens. So clicking on message number 1 and then 2. You see that when I click on message number 2, the button is even frozen. The focus is not even shipped over to message number 2, which means that the event handling of this is being blocked by event handling of the first event handler, because all of these are using one single thread. That's why clicking on this is being blocked by the first one. But eventually, second message is being displayed. Right? That's because the IO device has a queue, has a separate queue, the queuing my click event. And then once the main thread releases the first event handler, it processes the second event handling. So if I go back and forth, message 1 and 2, and then 1 and 2, and then 1 and 2, you will see that all of them will one by one be displayed because every click is being queued inside the IO processing queue. That's not so important. What I want you to focus on is that when I click on message 1 and then message 2 immediately, this clicking is being blocked. Let's watch that again. So clicking on the first one and then try to click on this one, the interface is frozen. So each one of this task can be considered as a big fat task. I'm going to actually code a function to represent the showing message fat task. And I'm going to have a parameter here, and then I'm going to move this over. So here, I'm going to assign message to it, and then the delay is passed over here. Now, before we use thread, I want to show you something. So I'm going to call this again, message, and this is going to be first message. And the delay is going to be, let's say, 3 seconds. And then this one is going to be the second message. And let's delay this for 5 seconds. Okay. And let's run this simple application now. And if I click on the message number 2, when I do this, and if I try to see, I'm trying to grab this window, it doesn't move until this message is displayed. That means the long running task is finished. Now I can move this. Right? When I go click message number 1, I still cannot move this until the message is displayed here. So you can see that this is one thread and the long running task is blocking. So in order to fix this issue, we're going to use a different thread. I'm going to offload this task to a different thread for each one of them. Let's see, instead of removing this, let's just keep it here. And then remember how to start a thread. We're going to declare the thread first and then assign a task to it. But this time we cannot just say show message because the show message method actually contains parameters. So in order to supply the parameters, we can use lambda expressions, or we can call it arrow functions. And here we can call this show message method. And I'm going to do the same thing here for the second one. I'm going to copy this and paste it over here. Change this to second message and this one to 5 seconds. Okay. So if you're trying to foresee what's going to happen, the thread is going to be started when we call thread.start. But because this is offload, right? This big task is offload to a thread. The main thread, which is the UI thread, is not going to be blocked anymore. Although each task is still going to take a very long time, but because the task is offloaded to a different thread, then the main thread is not going to be blocked. So let's run application now. And now if I click on the button, I'm going to see something different. If I click on the first one, I can immediately move the window, and then you notice that the first message is being displayed. Click on number 2, I can still move, and after 5 seconds, the second message is being displayed. So I can switch back and forth between the buttons, and it's not going to be frozen. You're going to see that the focus changes from one button to another. It's just that the message is not going to be displayed until the time comes. So let's try that. Message 1 and 2, 1 and 2, 1 and 2. You notice that the color changes, which means the focus changes. It's not being blocked, but all of the clicking are being coded in the IO processing queue, and each task takes a long time to finish. So this is the concept of offloading a long-running task to a different thread. And we often call this worker thread. And the purpose of that is so that it doesn't block the main thread. And that's usually the case when you have a UI application, which means that the user is waiting, and we don't want the user to wait for a long time. Therefore, we use threads to offload work to the worker thread, right, instead of blocking the main thread. And that's everything I want to cover in this video. Any questions, please let me know. If not, I will see you in the next one. This is assignment video. In this video, we're going to handle a type of problems which is divide and conquer. We have done that before, but this is an assignment for you to do. So we're going to simulate a web server that handles concurrent requests. So for a web server, let's use a rectangle to represent the web server. When the user interacts with the web server, the user basically sends a request to the server. The problem with the web server is that it's exposed on the internet, so everyone is able to access it. So most likely, you will have not only one user, but multiple users. And some very popular web servers could have millions of requests per minute or even per second. So let's just use 2 users to illustrate the scenario. So when the requests are received on the server, what's supposed to happen is that first, the web server need to enter these requests into a request queue. So let's use these little squares to represent the requests that are queued in the request queue. Second, there has to be something that is monitored queue. So let's say this is the monitor request queue. Once the monitor sees a request, he needs to let someone to process the request. So you would have something, maybe we can call it request processor. So these are the essential elements of a web server. Requests are coming in from multiple users. They're queued in the request queue. And then there has to be a monitor that constantly monitors the queue. Once there's a request coming, the requests are assigned to the request processor. So this is going to be a console application. Don't worry about processing HTML. Don't worry about processing anything. Just use a console application to simulate the web server. Right? And you're going to create a console application that accomplish the elements that I illustrated on this diagram. But first of all, let me show you how it look like and how the performance is if we were to do this in a single thread. Right, so I only have one thread here. As you can see, first we say server is running, please type exit to stop. So then we enter a non-stop loop. And within it, I'm going to try to read a line from the user. If the user enters exit, then the loop is going to stop and we're going to exit out the program. Otherwise, it's going to process. And this process method is right here. And we're using a thread.sleep to pause the thread for 2 seconds. So this is to simulate a longer processing time. And after that, we just simply output processed input. In the assignment that you're going to work on, you're going to use the same process input. Okay? So this is your processing, but you have to implement your own monitoring. You have to implement your own processing. You have to enqueue and dequeue the requests while you're monitoring and processing the requests. If we were to run this, you're going to notice that the read line here is blocking. And then after a longer period of time, right, 2 seconds, this is output, then the console is ready for another user input. So during this entire time, everything is blocked. Nothing else can be processed. So let's run the application. All right, it says server is running, type exit to stop. So I'm going to say A and then I hit enter. And it says processed input is A. That's after 2 seconds of wait. So if I say B and then I try to hit B, I try to hit other things. See, I'm trying to continuously enter one single letter at a time. Now I just stopped entering anything. And you can see that every time it just waits for 2 seconds. Right? So the performance is like that. Apparently, there is a I/O queue that is separate from our program. So while I'm talking, it's still trying to process whatever that is entered into the I/O queue. Okay, I think it's done processing. The last input I entered is actually ADF. Right, so you have seen the performance. It's pretty slow. It takes 2 seconds at a time, and then during that time, everything's blocked, except the system I/O queue. Right, so your task here is to follow this diagram, and you need to have all of these elements. You need to have a request queue, and then you have to have a monitor that monitors request queue, and whenever there's a request that comes in, you assign that request to the request processor. Okay, try to work on this yourself. And in the next video, I'm going to show my solution to this problem. All right, let's work on this in Visual Studio. Remember, we have 3 different tasks. One is to enqueue this, enqueue the request into the request queue. Secondly, we need to monitor the queue. Thirdly, we need to process the request. So 3 different tasks. So let's jump into Visual Studio. This is the one that we created for the single thread scenario, which is still relevant. We're going to keep this function as this, and we're no longer calling this function from the main thread. From the main thread, we still need a while loop, like an infinite loop like this, to enqueue the request. Here, we just listen to the input. And once we have the input, we enqueue the request into the request queue. Because of that, we need to create a queue. Let's go to the top, and let's declare a queue. And we're just using a string inside the queue. And here we just create an empty queue like that. Now we need to perform the first task, which is to enqueue the requests. Here in the main thread, that's when we enqueue requests. That's the first task that it performs. So inside the infinite loop, if the user didn't type exit, then it needs to enqueue the requests. So the input queue, or maybe let's change the name to match the diagram that I provided previously. So I'm going to call it a request queue, and let's use this variable. And here we're going to say enqueue, and we provide the input into it. And that's everything we do in the main thread. The main thread is only handling this particular aspect. When the request comes, put it in the queue. Secondly, we need to monitor. And for that, we can provide a method. We don't necessarily need a static keyword like this. So we're going to say monitor queue. So here, basically, we need another infinite loop. So we cannot just monitor once and quit. And we need to continuously monitor. So when we look at the queue, we're going to say request queue. So if the count is greater than 0, that means there's some elements in there. Then we are going to first take that input out, right? So we take that input out of the request queue by calling the dequeue. And then we need to start a new thread to process this input. We cannot just directly call it like process input and provide the input this way, because if we do it this way, then the monitoring will be blocked by processing. Because we have those 2 different tasks. The monitoring and the processing are 2 different tasks. If we combine them, then the monitoring will be blocked by the processing. So therefore, we need another thread. So we're going to say thread. Remember how to declare a thread. So we're going to call it processing thread. And the thread will complete a task is to process the input, and then we just provide input like this. And right after that, we can start it. Now here, because a new thread is spin off, so this thread is not going to be blocking this while loop. So therefore, this while loop will go very fast, super fast. It's going to be super fast, which is potentially packing the CPU. So we don't want to add burden to the CPU. Therefore, I want to add a little bit sleep time for this. Let's add maybe 100 milliseconds of sleep time so that it doesn't bother the CPU that much. We don't want to consume all of the resources. So that's monitor queue, the second task. So the second task needs to be performed by another thread because the main thread is working on reading the input from the user and enqueue that to the request. So the monitoring task will have to be performed separately from this. Otherwise, the enqueue task will be blocking the monitoring, and the monitoring again will be blocking the enqueuing. So we don't want to do that. Therefore, we will have to use a different thread to monitor the queue. But we cannot do it here because the code will never reach here. We cannot do it here because this part is the main thread. So we have to do it before we enqueue the requests. We have to do it here, although this is the second one. So the second task is to start the requests monitoring thread, or the request queue monitoring thread. So we're going to have another thread. I'm going to call it monitoring thread and create a new thread, and the task is monitor queue. The monitor queue method doesn't take any parameters, so I can directly use it as a delegate. Now I can say monitoring thread .start. Of course, when this just start, there's nothing in the queue. It will be 0. Therefore, it's going to just sleep for 100 milliseconds and then come back. While it's doing this, because it's started in a different thread, so it's not blocking, and we're going to directly go to the enqueue request task, which is waiting for the user to enter the input. Now, the first and the second task are done, and the third one is to process the input. We already have the method here, and that is already being called by the monitor task. Right here, we're performing the third one. So add a comment here and say third one is processing the request, and this is being done by a different thread right here. Okay, so we have 3 different tasks being performed by 3 different threads. Right? We have the main thread working on the enqueuing of the request. We have a worker thread working on monitoring the queue, which is this thread. And then we have the third thread, which is also a worker thread working on processing. Now let's run the application and see the performance. Okay, it says server is running. Now if I say A and then hit enter, and it says process input A. So it still wait for 2 seconds, right? So because we have this 2 seconds. If I just do 1, it feels like the same as before. But if I continuously hitting the keyboard, so like this, then you see that they're being processed pretty quickly, one by one. And also our input is not being blocked. So I can do all of this all together, and then the processing is being done simultaneously. It's just that each process takes 2 seconds. That's why it appears to be slow, but at least it's not actually blocking the input, right? So the input is not blocking the processing is not blocking the input, and that's a simulation of a web server. One thing I need to point out before I finish this video is that we're using a normal queue. So this normal queue could be a problem in a real life scenario. If the enqueue operation here is in the main thread and the dequeue operation here is in the worker thread, if they're called in parallel, which they are, right? Here and here are using different thread. This is the main thread and this is the worker thread. It's possible that they're being scheduled by the thread scheduler in different core of the CPU. So at that moment, they are actually being run at the same time. That's true parallelism. So if they're really called in parallel, it can lead to a race condition and unpredictable behavior. This is because the regular queue class is not thread safe. So this is something we're going to talk about in the future when we talk about thread safe collections. But in this exercise, we can just use regular queue to implement this assignment. It doesn't really cause any problems because we are manually entering from the screen. Right? It's going to be, it is actually pretty slow. The chances for different threads to enqueue and dequeue at the same time are pretty low. So it's not going to be a problem. But when it's in the real world scenario where you have a lot of requests coming to the server, you have too many threads run at the same time, and there's always a possibility of enqueuing and dequeuing at the same time. And if you use regular queue, it might lead to unpredictable behaviors. And we're going to talk about synchronization later. Okay, that's everything I want to cover in this video. If you have any questions, please let me know. If not, I will see you in the next one. In the previous section, we have talked about multi-threading programming a lot in C#, and you have seen the basic syntax. They are not so complicated, but what's getting complicated is that when we are using multi-threads to perform tasks, But performing these tasks require multi-threads to share some common resources. When we have these kind of scenarios, things will get complicated because sharing resources may run into conflicts. That's not only human nature. It looks like computers are just extension of our human brains, so they have the same problems. Let's take one of the examples that we had in one of the previous videos. So sharing the kitchen for cooking the dinner, we have dad and mom split all of the dishes in half, and dad cooks half of the dishes and mom cooks the other half. However, when both people are in the kitchen, most of the resources are shared. For example, the common space is shared, the cooking surface is shared, some of the tools are shared, like cutting boards, knives, the spices are shared, the cookware are shared. So if we don't actually arrange things properly, mom and dad may run into conflicts. The whole cooking process may actually slow down because of the conflict. Let's take another more concrete example. Let's think about a bank. Right? So if this is a bank building, and we have two people sharing the same account. Let's call them Tom and Jerry. They have the same account. Let's say that in the account there's $1,000. Tom comes to withdraw $800 and Jerry comes to withdraw $800 as well. They didn't communicate with each other. They just come separately to the bank without knowing each other coming to the bank. And they're both withdrawing the same amount of money, which is $800. And when they come, there's teller A and teller B trying to help Tom and Jerry separately. Now, if the bank didn't implement any procedures to synchronize the process, and if teller A and teller B are not communicating with each other, let's say Tom and Jerry came to the bank almost at the same time, and teller A and teller B trying to inquire the balance of the account at about the same time. Now, because when teller A look at the account, it's $1,000 left. And when teller B look at the account, there's also $1,000 left. Imagine that this is before computer time. Because of that, teller A sees $1,000 is enough, right? Because Tom only asked for $800. Teller B also sees there's enough money, and he knows that Jerry wants only $800. So what's going to happen is teller A is going to give Tom $800, and teller B is going to give Jerry $800. Now, who's suffering? The bank is suffering because the account is overdraft. At this moment, negative $600 in the account. So this is a classical example where two different threads are performing tasks that are based on shared resources. In this case, the shared resource is the bank account. So if there's no proper arrangement to synchronize the processes that are performed in parallel, then there is going to be a problem. And this proper procedure that's required to help to solve this type of problems is called thread synchronization in computer programming. So this is a real life example. And now we can jump into Visual Studio and look at how this problem manifests in computer language. Let's go ahead and create a new project. Still a console application, click on next, and we're going to call this Synchronization Overview, .NET 8, and we have a blank application now. So what we are trying to do is to add 1 to a counter, and we're going to have a counter, and we're going to initialize to 0. So this is going to be shared between two different threads. And what is the task that the threads are trying to perform? It's going to increment the counter. So I'm going to create a function to represent the task, and I'm going to call it increment counter. When we increment, we're going to increment it for 100,000 times. Here I'm going to say counter equals counter plus, not plus I, but just plus 1. Okay, so easy and simple. So this is the task the threads are going to perform. So now let's go back to the top, and we are going to declare two different threads. So thread 1 is going to perform the increment counter task. And we're going to have the same thing, which is thread 2, it's also going to perform the same task. Now, if we let them perform the task one after another, which means that we're going to let the threads run synchronously, we're going to let thread 1 perform first, right? So let it perform first, and then we block. So we use thread 1 join to block it, so that thread 2 cannot start until thread 1 finishes. So here I'm going to say thread 2 start. And when thread 2 finishes, then what we're going to do, we're going to console and output the result. So the final result, I'm going to say the final counter value is counter. And that's it. So if we do it this way, everything runs synchronously. There's nothing special about this. And the expected result is going to be 200,000. So let's run it. And as you can see, it says the final counter value is 200,000. However, if we let the thread actually run asynchronously, so let me move this line down over here. And then I'm going to put these two close. So we're going to have thread 1 and thread 2 start one after another. But as you know, the worker threads are not blocking, right? This worker thread is not blocking. So once we have these two lines going, the threads, they're going to work in parallel. And then here we're just blocking so that after both threads finish, we are going to output the result. And this time, before I actually run it, what do you think is going to happen? Is it going to show 200,000, or is it going to show more than 200,000, or is it going to show less than 200,000? Let's run and see the result, right? This time, you can see that we have less than 200,000. If I run it again, now the value is different, but it's still less than 200,000. So why does that happen? Nevertheless, we're executing this line 200,000 times. That's absolutely correct. Whether there's any conflicts, synchronization problems, this line will be executed 200,000 times. However, the result is less than 200,000. So what is happening here? Because these two threads are running at the same time. So this is very similar to this bank account. The teller A and teller B, they are working at the same time. And when they look at the account, they see that there's $1,000 left. They see the same value. And they both think that there is enough money in the account. Same situation here. Let's say that this counter is sitting at 1,000. And at this moment, both thread 1 and thread 2 are looking at the counter value at about the same time. Then they're going to see that the counter value is 1,000. So then thread 1 add value 1 to it, which make the counter 1001. Well, thread 2, guess what? Also add 1 to it, which makes the counter also 1001. It's probably not so easy to understand. The key problem here is this assignment is not an atomic operation. There are two steps involved in this line of code. The first one is it's taking a temporary value from the counter, right? So it's reading the value of the counter. The second one is that it tries to increment 1 based on the value in the temp variable. Let me copy this code and let's go to the diagram. Let's use the diagram to help us understand what is actually happening now. So we have this in thread 1 and we have the same thing in thread 2. Okay, because thread 1 and thread 2, they're running about the same time in parallel. So it's possible that both are executing this line. var temp equals to counter. So var temp equals to counter, they get 1,000. The other thread also get 1,000. But the thread scheduler at this moment prioritize this first thread. So counter now becomes 1001. And then it's the second thread turn. At this moment, the temp variable is still 1000. So now the counter equals 1000 plus 1. So it is still 1001. That means although these two lines are executed twice, but the result is that the counter didn't increment by 2. The counter variable still increment by 1. But it doesn't actually happen all the time, right? If it happened all the time, then the counter will probably just sitting at very low value, depending on how many times this particular situation happens. That determines the final result. So from this example, you can see that whenever two threads are sharing the same resource, the program may run into problems. And we call this type of problems race conditions and inconsistent behaviors. It's inconsistent because you have seen that every time when I run it, the final result is actually different. Although they're less than 200,000 almost all the time, but they're still different. And race conditions is due to the threads are interfering with each other because they're trying to use the same shared resource. So this is how it manifests in computer programming. Therefore, we need a technique to solve this type of problem, and the technique is called threads synchronization or simply synchronization. We are going to talk more about this technique in the rest of this section. And that's everything I want to show you in this video. If you have any questions, please let me know. If not, I will see you in the next one. In this video, we're going to talk about critical section and atomic operation. In the previous video, we used this increment counter program to demonstrate the synchronization problems that we're potentially going to run into when we have multi-threads running in our program. So this increment counter function are being called in separate threads. And you have seen that what is really causing the problem is about this area. What is special about these two lines of code? These two lines of code are accessing the shared resource, which is the counter variable. So if we look at our program again, we are dealing with the counter. Basically, this counter equals counter plus 1. When the compiler compiles it, it's actually separated into two different lines, right? This one and this one. And they're both accessing the counter variable, which is defined outside of this thread. Unlike this integer I, this is defined inside the thread. So even though multiple threads are being used here, each one instantiate the I variable separately in their own space, whereas the counter is the shared resource. Therefore, this section that access the shared resource becomes critical, and we call this critical section. That's the concept of critical section. And then we're going to move on to the next concept, which is atomic operation. What is really causing the problem within the critical section is that this particular line of code is divisible. It's actually two lines of code. But imagine that if this line of code cannot be divided into two, right? It's indivisible. Then there's going to be no problem. So if these two lines of code, let me highlight it. If the code within the critical section is being executed as one step instead of multiple steps, then even though we're using different threads to execute the code, let's say thread number 1 execute first, the counter 1 will be increased by 1. And then when thread number 2 executed, the counter value will be based on the new counter value instead of the old counter value, right? So in the previous video, we were saying that the counter is sitting at 1000. So in this case, if the thread scheduler favors thread number 1, and the code inside the critical section is being executed as one step instead of multiple steps, then thread number 1 will increment the counter value from 1000 to 1001. And then when it's the second thread's turn to increment the counter, it will see that the counter value is sitting at 1001. Therefore, it's going to increment it again and becomes 1002. So there's no problem whatsoever if the code within the critical section is running as indivisible step. There's just one step instead of multiple. Then there's no problem. The problem is really that, first of all, we have a critical section, which means that shared resources are being accessed within multiple threads. Secondly, the operation within the critical section is not atomic. It's divisible. Because the definition of an atomic operation is that the operation itself is indivisible. It cannot be divided into multiple steps. It's always going to be executed as one step. If the operation within the critical section is not atomic, and in that case, we are going to run into synchronization problems. And what we need to do is to find a technique to make the visible code within the critical section indivisible. And that is what we are going to cover in the rest of this section. And that's everything I want to talk about in this video. If any questions, please let me know. If not, I will see you in the next one. One of the synchronization techniques is called exclusive lock. The basic syntax of the exclusive lock is basically just saying lock and then parentheses. So within the parentheses is a lock object. We're going to talk about when we jump into Visual Studio. And then you use curly braces to surround the critical section. We call everything within the curly braces the body of the lock. Right? So everything that is within the body of the lock is usually the critical section. And when you apply the lock this way, the body of the lock can only be executed by maximum one thread. No other thread will be able to access the code within the body of the lock while a lock is being held by another thread. So this essentially makes the operations within the body of the lock atomic. Although they're divisible, but it's as if they're atomic, just because they can only be executed by one thread. So let's jump into Visual Studio and see it in action. So in order to apply the lock, first we need to have a lock object. I'm using .NET 8. In .NET 9, things is slightly different. But in .NET 8 or previous versions, which is C#12, including C#12, what you can do is you can just declare an object like this. And you're going to say counter lock. And you can just say new object like this. Now, this can be used to lock a critical section like this. So now let's go to the critical section right here. And then we can say lock. And then we apply that to the counter lock. And we use curly braces to specify which is the critical section to be included in the body. And it's just like this. It's very simple. Now, when we do this, this code can only be executed by one thread. It's not possible that both threads are executing this. Right? And it's going to avoid the problem that we had before. All right, so let's run this and see what happens. All right, now you can see that the final counter value is 200,000. Now, if I run it again, it's going to be the same thing. See, every single time it's going to be 300,000. And that's just because we applied the exclusive lock. And it's as if this line becomes an atomic operation, although it's not. But we are using the lock to make it behave like atomic operation. Now, one more thing I want to mention is that the lock has within itself a try-catch mechanism, try-catch and finally mechanism. That means that you don't have to worry about what if inside here, because this is just one line of code. In real-world project, you may have complicated operations within the body of the lock. And what if it throws exception? You may worry that if it throws exception and the lock is not released, then other threads won't be able to get the lock and everything is blocked. You don't actually have to worry about that because within the lock, there is a try and finally mechanism there. So inside the finally section there, the lock is always released. You don't have to worry about releasing the lock when you use the lock keyword. And another thing, as I mentioned, in C#13, which comes with .NET 9, and it's still in preview at this moment. I haven't installed it yet, but in there, what's recommended is that instead of using an object, you use system.threading.lock. I think it's called that. As you can see that it's not actually available in my version because I'm using C#12. So I have to do, I think it would be look like this in C#13. So I have to do what is recommended by the previous versions. Right? So I'm just using a object here. This can be any reference type. It doesn't have to be an object. And the best practice is to use a dedicated lock that has only one purpose, which is to protect the critical section here. And I think that's everything I want to cover in this video. If you have any questions, please let me know. If not, I will see you in the next one. This is an assignment video. We're going to practice using exclusive locks by creating an airplane seats booking system. Probably have used the online tickets booking system from airline companies. This type of system will definitely have to be multi-threading in order to improve performance. And because of that, you will have to pay attention to threads synchronization problems that may potentially happen. For example, if there's only one ticket available, let's say only one ticket available, and if at this moment there are two people online trying to book ticket, if you don't apply locks, if they come at the same time, the first person will see that, oh, there's a ticket available. And the second person also sees that there's a ticket available. And then both click on the book button around the same time. Then both people will get the ticket. But when they come and trying to board the plane, that's where problems may happen. I actually just experienced this in this month when I flight from Atlanta to Toronto. A person was sitting in my seat. When I came, she asked whether this is my seat or not. I said yes, and then she went down and started telling me that her seat was taken by another person. And she told me that they have the ticket, and the ticket is showing the same seat number, same date, same airplane. She was lucky because the airplane wasn't full, so she was able to get a spare seat. As you can see that this kind of problem actually happen in modern day airline companies' seats booking system. So let's try to create this seats booking system based on the web server that we created in assignment number 1. So if I come over here, this is what we created for assignment number 1. We have a queue, right, to queue the requests. Of course, when we modify this request queue is actually a booking request queue. And you will still have a monitoring thread will be monitoring the queue. Right? The main thread will be works on the enqueuing process. Monitoring thread will be working on checking the queue, checking the request queue, and try to process the request. And this processing is not just any processing. This is actually trying to book the airline ticket. And that's where the problem happens. That's where you will have to keep a counter of the available ticket. And that's a shared resource that will be accessed through different threads. And you have to apply a lock to the critical section. And that's how you do it with this console application. We're trying to use a console application to mimic a scenario where we have a web server available for users to buy tickets. All right, another thing I want to mention is that when user enters the letter B into the queue, that means the user wants to book a ticket. If the user wants to cancel the booking, he or she is allowed to do that, and she can do that by enter letter C. So this adds another layer of complexity. You have to handle both addition and subtraction from the available ticket. All right, try to do that yourself. And in the next video, I'm going to work on my solution. If any questions, please let me know. If not, I will see you in the next one. In this video, let's work on this airplane seats booking system. Let's go to our Visual Studio. This is the code that we previously wrote in for simulating a web server. And the part that we really need to change is about this process input function right here. So let's change this to process booking. Let's replace this as well. Okay, so now we need to think about whether tickets are available or not. Let's create a variable at the top. And we're going to say available tickets. And usually airplane is pretty big. Maybe you have 100 seats, 300, 500 seats. But let's just imagine it's a small airplane that only have 10 seats available for booking so that we can try and run into different scenarios. Now, when we're processing the booking, of course, we're going to use this thread sleep to simulate a longer processing time. But here, we can't just output the result. We have to tell whether tickets are available or not. First of all, if the input is B, Well, actually, let's change the message first. So server is running, and then let's enter a carriage return, and then say type B to book a ticket, another carriage return, and then say type C to cancel. And let's maybe add another carriage return at the end so that the messages are nicely separated from our input. We are going to check whether the input is letter B or letter C. So if it's letter B, then we do the booking, otherwise we do the canceling. So if the input is C, so it's automatically actually generating the code for me. Now inside here, I want to check whether the available tickets are there, right? So if it's greater than 0, then that means we have tickets to book. And first of all, we want to take away a ticket, right, as soon as possible to make sure that tickets are decremented. And then we are going to, let's write an empty line first. And then we're going to write another line. We're going to just say that your seat is booked, and we can output the number of seats available. So available tickets, we can say seats are still available, something like that. And then here, if we're canceling, then we're doing the same thing, but here, instead of decrement, we're going to increment the counter. And we're going to say your seat is canceled, or maybe say your booking is in available tickets, available seats are available. Okay, looks like we have a extra curly brace, so let's delete that. So now we implemented the code without locking mechanism. Therefore, we're going to run into synchronization issues, but I can't reproduce it because typing on the console is just too slow, and the chances of encountering risk conditions are very low. But if you have lots of people online, and there's going to run into coincidence where two people are booking at the same time. Therefore, we will have to use a lock. Because, as you know, the process booking thing here is in a thread, right? So there could be multiple threads running at the same time that is executing this process booking function. And because here we are reading the shared resource, which is this common variable here. This common variable is common through all of the threads, right? So this is the shared resource between all of the threads. So here we're reading, here we are reading and writing. And then actually, I think we need to also check, right? So if the available tickets is less than 10, then we are going to increment. We don't want to add more tickets to the system. So we're going to do this. So here again, we're reading. Reading is also pretty important because we are going to make decisions based on the number that we read. And here there's a reading and a writing, one after another. So therefore, all of these are considered a part of the critical section, except the output. Output is just for display purpose, but we can't get them out of the section, right? They're going to be part of our critical section. So if you want to be really accurate about it, you can use lock this way. So I'm going to lock object, which we will have to declare it right here. So we're going to say object, and we're going to say tickets lock, or you can call it seats lock, or whatever you want to call it. And then we're going to come over here. So if you want to be accurate, we're going to use this tickets lock around this if statement, and then another lock around here. But it doesn't really matter because things run really fast. We're just comparing the input with letter B and here with input with letter C. So we can apply the lock this way. Tickets lock, close that. And then I'm going to move this into the curly braces of the lock. So this becomes the body of the lock. And because we're applying a lock around the critical section this way, we're guaranteed that there's maximum one thread that is accessing the critical section. So this is going to avoid our race conditions. So let's run our application and see what happens now. Okay, it says server is running, type B to book a ticket, type C to cancel. So let's try C first. And nothing is happening. That's actually by design. We didn't spit up any message if the available tickets is greater to 10. So that's why it looks like nothing is happening. Now if we say B, then after 2 seconds, it says your seat is booked, 9 seats are still available. Now if I keep typing B, for some reason I just typed 10 different times. So let me try to do that more. Now you can see that nothing is happening anymore, because if we look at our code here, if available tickets are greater than 0, then we're booking, otherwise nothing is happening. So maybe to make it clearer, we are going to do something like this. So we're going to add a else statement here, and we're going to say console.writeLine, tickets are not available. Something like that. WriteLine, tickets are not available. Tickets are not available. Maybe add another one here. I'm just going to say error. Cannot cancel a booking. Something like that. Okay, run the application again. Now, if I say C at this moment, it says error, you cannot cancel a booking at this time. If I enter B, so this time let me enter B for many times. So I entered a lot, and you can see that your seat is booked, 9 available, 8 available, and it's decrementing until 0 seats are available. And then the message changed to tickets are not available. At this moment, if I say B, then after 2 seconds, it's going to say tickets are not available. But if I type on C, then it says your booking is canceled and 1 seat is available. I do another C and 2 seats are available. So I'm going to do a lot of C and see what happens. So it's going to add until we reach error, because I cannot cancel a booking at this time anymore because it's already 10 seats. It's full already. Now I can continue booking. So I can book and cancel and book and cancel and book and cancel. So if we come back and read the message, so I booked and then booked again, booked again, booked again. And now it's trying to process the cancellation. So it adds, so 6 seats available, then it adds to it, becomes 7 and 8. And then it's processing the booking again. So it decreases, and then increases. So you can see that the process is going pretty smoothly with the lock. So that's how I implemented with a lock keyword. I hope you had fun implementing this tickets booking system. If any questions, please let me know. If not, I will see you in the next one. In this video, we're going to talk about another thread synchronization technique, which is monitor. First of all, why do we call it monitor? You can consider it as an action toward critical section. So previously, we're using a lock to protect the critical section. So when we encounter a critical section, so let's, for example, use this block to represent a critical section, and the monitor represents the action that it monitors the critical section. Why it needs to monitor the critical section? Well, because it's critical. And why it's critical? Because the critical section includes the resources that can be shared within different threads, and because different threads can run in parallel, so they could potentially run into conflicts. That's why we call it critical section. And having a monitor to monitor the critical section, so that if one thread already entered into the critical section, other threads have to be blocked, have to wait. So that's why we call it monitor. Knowing this concept will help us to understand the syntax and make sense out of it. Otherwise, we'll just have to remember the syntax. Although remembering syntax is not difficult. Okay, let's continue with the syntax. But first of all, monitor is actually going to generate an exclusive lock, which is this exclusive lock that we have talked about. In fact, the lock is based on monitor. Okay, so it's basically a simple form of monitor. However, using monitor gives you more granular control than lock. So this is the basic syntax here. You can see we have a monitor.enter, we have monitor.exit. And in between of these two lines is our critical section here. So basically here, monitor.enter is trying to enter into the critical section. And here is trying to exit critical section. Now, once we're able to enter into the critical section, we actually generate a exclusive lock. So monitor.enter actually generate a exclusive lock if it successfully enter the critical section over here. So that no other threads will be able to enter the critical section. And then monitor.exit is always called at the end of the critical section in order to release that lock. However, if there is another thread that is already called monitor.enter and in turn generated the lock, then this monitor.enter will be blocking. So here, this is blocking, right? Until the lock is released by the other thread, then it will enter into the critical section over here. And we use the try and finally mechanism so that we are always calling the monitor.exit in order to make sure that we always release the lock that is generated from here. So this is the basic syntax of using monitoring. You can see that this sort of makes sense that we are using this word monitor to monitor the critical section, and then we enter into the critical section, and then we exit out of the critical section, and in between of that is our critical section. So this makes a lot of sense. Although I personally still prefer the lock, exclusive lock syntax over here because it's very, very simple. However, when you use the lock, the compiler actually compiles this code into this. So exactly like this. That's why when I talk about the exclusive lock, I was saying that there is a try and finally mechanism that's referring to this particular code. So this is the basic syntax of using monitor. If we jump into this particular example that we used before to increment counter, and because the counter itself is incremented by different threads, therefore this becomes a critical section. Especially this is not a atomic operation, and that's why it's a critical section here. And previously we were using a exclusive lock to protect the critical section. Now, if we were to change this to use the basic syntax of monitor, then it's still quite simple. We're going to say monitor.enter. We're trying to enter into the critical section by monitoring the lock. You can say monitor the section. You can also say monitor the lock over the section. Right? So both will help you to understand why we call it monitor. Now I'm going to change to a different way. I'm going to say we're trying to monitor the lock over this section. And if there's no lock, then I'm going to generate the lock. Right? So monitor.enter is monitoring this counter lock. And if we are successful, then we generate a lock over this critical section. Now we're going to use try and finally to make sure that at the end of the section, we always able to exit the critical section. And therefore, we're releasing the lock. So if we were to do it this way, this is exactly the same as lock using the exclusive lock. Right? So if we were to run it, I'm going to see that the result is 200,000. It shouldn't be less than 200,000. You can see that the final counter value is 200,000. No matter how many times you run it, it's going to be 200,000 because we're using monitor as a thread synchronization technique. Okay, this is the basic syntax. Now let's revert this back to using lock. So using lock in this particular example makes sense. However, if let me close this solution and bring up the ticket booking system or the seats booking system for airline company that we did in the assignment number 2. So if we look at the example over here, go to program.cs, we are surrounding the critical section over here with the lock so that only one thread can access the critical section at a time. That is what we did. And it has been working. However, there is a problem. Imagine that this is a real-world application. It is actually a web server and people are accessing this server through browsers. If for some reason it's quite busy, there doesn't have to be too many users to cause the problem. Let's say there are 20 users are booking at the same time. Then everybody is in queue and waiting. Right? So the chances for this to be released, for the locks to be released within 5 or 10 seconds could be quite low. And usually for a airline tickets booking system, waiting for 5 seconds or 10 seconds without being notified of what is going on is quite user unfriendly, right? Not friendly. So sometimes we want to provide a message in between to let user know that the system is busy and try again later. There's different mechanism you can apply to it, but usually it involves a notification, and that notification can only be applied if the thread is not blocked, right? If you're still blocked, how can you display a message to the user? That's why the monitor has another feature, which is a waiting timeout time. So instead of using the lock, we can try to use monitor. So here we can see monitor dot. There is another method, it's called try enter, and this one takes different signatures. So there is one, you can see that there is a milliseconds timeout. Let's say that in order to simulate it, we increase this to 10 seconds processing time. And then this one would be 2 seconds wait time. This is not realistic, but in order to trigger the scenario, I'm going to do it this way. Basically, we're trying to acquire a exclusive lock, but we're only going to wait for 2 seconds. If there is a lock that is already required by some other thread, then I'm going to wait for 2 seconds. And then this is going to return us false. See, this return value says true if the current thread acquires a lock, otherwise false. So when this returns false, that means we didn't succeed in getting a lock. So therefore, we cannot enter the critical section. So we're going to use a if statement. And of course, if we successfully acquire the lock, then we enter into this critical section. And else here, we're going to console and write line, we're going to say the system is busy. System is busy. Why we say this is because we didn't get the lock, right? Someone else is still executing the critical section. Therefore, we cannot enter into the critical section and we time out. So we can say the system is busy, please wait, something like that. This is not very user-friendly. A better way to actually do this is to have a loop. Okay, so if this fails, it's going to try again. But at least when we use try enter, we have a timeout. We can use the timeout to output a message, make it more user-friendly so that the user is notified that we're still trying, but in the meantime, our system wants to let you know what is happening. Right? Instead of making the user waiting the whole time without any message, by using the try enter and providing a timeout, we are able to notify the user about what is happening. So that's the good thing about using monitor as opposed to exclusive lock. Both create exclusive lock and hold on to the exclusive lock. Don't forget here that we need to release the lock. And where is that? That's in the critical section over here. We're going to do a try and catch. Try and finally, we're going to move this, or actually move this curly brace down over here. And then we're going to say finally, we are going to release the lock by saying monitor.exit tickets lock. Okay. Now that we have increased this to 10 seconds and wait time to 2 seconds, I think we're still not able to output this notification. It's because the processing starts at the very beginning and the wait is over here. Okay, so we have to move this line down. So the processing is usually within the critical section, so that it's part of the critical section. This time we should be able to see the system is busy, please wait. And let's run the application and see what is going to happen. All right, let's increase the font a little bit, and I'm going to keep enter letter B to generate a lot of booking in the queue to simulate the situation. So I'm going to generate a lot of B like this, and you can see this is the system is busy. Please wait. So we need to wait for 10 seconds. And finally, there is one that completed the booking. So maybe our wait time is processing time is too long. Maybe change this to 3 seconds processing time. And let's try again. So lots of B's, and now you can see that we have multiple, at least 2 bookings are successful, other ones are being blocked out. Right, that's why I was saying this is still not user-friendly. Better way to do it is to have a loop, right? Loop around the critical section so that it's going to repeatedly try to enter the section, but at least it gives us an opportunity to output. Okay, that's everything I want to cover about using Monitor for thread synchronization. If any questions, please let me know. If not, I will see you in the next one. In this video, we're going to talk about Mutex. Mutex is another thread synchronization mechanism that is used to help us to protect a critical section. It's very similar to a lock or a monitor, that we're going to create some sort of lock around the critical section in order to protect it. But usually we don't call it a lock, we just call it mutex. And its syntax is very, very similar to a monitor and looks something like this. So first, we create a mutex. It's a little bit confusing here. By creating the mutex, we don't actually have ownership of the mutex yet. So in order to have ownership of mutex, we're going to use mutex.wait1. Once we have the ownership, the thread is going to proceed into critical section over here. And after that, we don't forget to release the mutex. So very similar to monitor, right? In monitor, we enter the critical section and then we exit. Here, we use wait1 to acquire the mutex, and then we enter into the critical section. And then here, we release the mutex. So some other thread can acquire the mutex. So you may ask, if we already have monitor and works very, very similar to monitor, why we need mutex? Well, one of the distinct features of mutex is that it can not only be used within the process, it can be also used across processes. And for that, we need to cover some basic concept of process in case that you don't know about it, because at the very beginning of this course, I mentioned that we have this diagram here, we have application, and then we have threads. Okay, so I was using the rectangle to represent a application, and I was using the little circles to represent different threads here. So I was omitting on purpose another layer in between, which is process. So let me make that clear in this video. But first of all, we have something called application. And then within the application, we can have different processes. For example, this application have 2 different processes, and then each process can have 1 or multiple threads. So in this example, the first process only has the main thread, and the second process have actually 2 different threads. So there's 3 different layers: app, process, and threads. But in terms of learning about multi-threading, it's not very important to know about there could be possibility of different processes, except in this particular lesson. Why we could have different processes within one application? Well, let's look at this task manager for now. So task manager, if I order by name, I can see different applications at the top. And then if you see, for example, there's a bracket and there's 3 in it. This means this application has 3 different processes. And then for Outlook, there's so many. And then for Microsoft Edge, you can see that we have 16 different processes. And the reason why we need different processes, there are different reasons. One of them is to improve the performance. For example, for this browser, modern browsers, each tab could have its own process. And then each extension has its own process. So from architecture point of view, this is going to be better separation of concerns. And from performance point of view, this could be allowing the browser to utilize multiple cores of modern CPUs more efficiently. So therefore, we have to be able to deal with multiple processes within the same application, right? And with multiple processes trying to access the same resource, for example, a file, then although it could potentially increase the performance, it could potentially cause race conditions in the same way as resources shared within different threads. But we can't use monitor or lock anymore because those synchronization techniques can be only used within the same process, then we have to use particular type of synchronization technique. For example, in this case, we use Mutex because Mutex can be used to lock shared resources exclusively across different processes. However, the syntax is slightly different. So this syntax is actually used only for local Mutex. You cannot use this Mutex across different processes. But if we slightly change it, then we will be able to use it across different processes. And the way to do that is to have the first parameter passing as usually as false. So this is the initial ownership. We don't need to worry about this for now. We drag this, okay? And then the second parameter is important. The second parameter is the name of the Mutex. So you can give it a name. So when you give the Mutex a name, this Mutex can be shared between different processes. So for example, I can call it global file Mutex, something like that. You can give it any name you want. And then nothing change over here within the using statement. Another thing you notice that we're using the using statement. This using statement is very important because we want to dispose the Mutex at the end. Why we want to dispose the Mutex? Because this is a resource within the operating system. It's like a file. So you want to dispose it. You don't want to leave it in the operating system, and that could lead to potentially memory leak. Now let's look at some examples. Okay, so let's take a look at our counter example. So in this synchronization overview example here, we are using the increment counter. I've been using it for many times. And we are just basically incrementing the counter variable, which is a shared resource. And we're using 2 threads to increase it. And there's always a possibility that they're going to run into risk conditions. So the inconsistent behavior will be the result. And the counter, although expected to be 200,000, because we're using 2 threads doing the same thing. So when 1 thread finishes, it will be 100,000. When 2 threads finish, it's supposed to be 200,000. But if we run this, it's almost always less than 200,000. You have seen that. And as soon as we use a lock to protect the resource, the result is consistently 200,000. Now, if we change this to do the same thing in 2 different processes, of course, we cannot use memory. We cannot use this. This is also always a memory within the process, right? So this cannot be the shared resource. So we can use a file to store the counter value. And then when we increment, we first read the counter from the file. And then after we increment, we write the value back to the file. That way, the file becomes the counter, the shared resource. In each process, we just need to loop through not 100,000 times because opening and closing files taking too much time. Maybe we can try 10,000 instead of 100,000. Okay, so let's give it a try and see what happens this time. So let's close this solution and try to create a new one. So again, same thing, console application, and we're going to call it Mutex example. And maybe making it more specific, we're going to have global Mutex because local Mutex is almost the same as monitor. .NET 8 long-term support. Now delete the default lines here. So what are we going to do? We are going to create a file path, and I'm going to just call it counter dot. So it's going to be a text file. Now I'm going to loop through a index for how long? How many? 10,000 times. And each time I'm going to get the counter out from the file. I'm going to say read counter, which is a function I'm going to create later. So I'm passing the file path, right? And then now I'm going to increase it. So this is, I'm writing everything without any thread synchronization mechanism. And we're going to see what happens if I run it. Right? So then I'm going to call write counter, write back to the same file. and with the same file path, and the counter value has to be in the parameter. Okay. Now at the end, I'm going to say console.writeLine, and I'm going to say process finished, and then I'm going to have a console.readLine, just so that we don't accidentally go out of this, finish this. Now we can implement the read counter and write counter. I don't want to implement it by just writing every single letter. I have prepared the code already for you, and we can go through that when I paste it over here. All right, so this is not a IO or basic C# course. That's why I just pasted it over here. So we basically have a read counter and write counter function implemented, and we have the file stream, and we allow different processes to open at the same time because file share is read and write, right? And then we open the stream and read the content and then parse the content. Same over here with writer content. We have the file stream, and then we create a stream writer. So this one is stream reader, this is stream writer, and then we write the counter value back to the file. Okay, so if I run it, basically let me build it first. Remember, the file mode here is open or create. So if it doesn't exist, it's going to create. If it does exist, then it's going to just open the existing file. So let me go to the file explorer here, and now let's go to bin, debug, .NET 8. Now I have this global mutex example, and I don't have the counter.txt file in the folder yet. If I run it now, it's going to take a while because we're opening and closing the file all the time, right? Closing and opening the file all the time. Now it's finished. So it's about 10 seconds to finish. And the result is 10,000. So that's expected. So now, what if I run? So let me delete this first. What if I run two different instances of the same application, which means two processes are running separately, and then I open up again. You can see that two processes are running, and they're reading and writing to the same counter file. Each one would do it for 10,000 times. The expected result is 20,000, right? But moment of truth. Let's open counter file. You can see it's way less than 20,000. And why? Well, it's the same reason that we have seen before within the same process, right? When we have two different threads running, we experience the same situation. Now again, if I delete it and run it again, so the result will be different, but it will be always less than 200,000. Let's wait for about 10 seconds, maybe a little bit more than 10 seconds, because we're trying to open the file and closing the file at the same time. Okay, the application finished, and let's open. This time it's even less. Now the reason why is that because the file itself is a shared resource, and accessing the shared resource from two different processes simultaneously will cause risk conditions and inconsistent behaviors. Therefore, we need to apply some kind of synchronization mechanism. Using monitor wouldn't work. Using lock wouldn't work. Let's actually try that. Okay, so let's say I'm gonna just use a lock to protect it. So we're reading and writing, so all of these should be a critical section. And let me declare it. So I'm gonna say file lock object. Now I'm gonna just lock the file. Okay, lock the critical section. And let me build it again and go over here. So I'm gonna delete the counter file for now, and let me run it and run it again. Let's wait for a while. It's going to be about 10 seconds. First one finished, second one finished. And let's close the processes and go to the counter. Now you can see that it's still less than 200,000. This time it's even less. So let me close these. That means the lock doesn't work. And of course, we don't need to try monitor because lock is monitor. I explained before. So let me delete this line and let's try to implement Mutex. So let me delete this as well because it doesn't really work. And I'm going to do a Ctrl+KF to format it, but I'm going to comment it out for now. So what are we going to do? We're going to use using statement. Remember, you have to use using statement in order to make sure that it's disposed the mutex is always disposed. And then we're going to go mutex. And you can see that there's different signatures. We're going to use this third one. But you can rate this initially owned. So if it's true, then it gives the calling thread initial ownership. We don't need initial ownership. That's why I'm going to use false. And then the second one is the name of the mutex. I'm going to just call it global file mutex. And in order to make a difference, perhaps I'm going to just add the file name here. In case some other people also create a mutex with the same name here, right? Because it's going to use across the operating system. So that's why I need to add the file name here, just to make sure it's always unique. And then within the using body here, I'm going to loop. So I'm going to just copy this and paste it over here and comment it. So in loop for, again, 10,000 times. But remember, this is the critical section. So before we enter the critical section, we need to require the mutex. And then we're going to try over critical section. So finally, we need to release the mutex. Don't forget to do that. Otherwise, we're going to be in trouble. All right. Now we have this mutex protecting us. I want to emphasize again, as soon as you give the mutex a name, this mutex becomes global across all of the processes. So this mutex now can protect shared resource across different processes. And let's give it a try. Let's first build the solution. And now go to the folder, delete the counter again, and let's run application twice. All right, so we have two processes running at the same time, and let's wait and see what's going to happen. It's going to take a while again, and thank you for waiting, but it's going to worth it. Now you can see actually it's taking a little bit longer because it's really kind of open and close at different times now. And it's finished, and let's go to counter, and we see 20,000. This is the expected result. No matter how many times you run it, you're going to have the same thing. Let's delete the counter.txt and just try it again. So this time I can try for 3 different instances and I expect to see 30,000. So if it works, it's going to be 30,000 instead of 10,000 or 20,000 or any number in between. So let's wait for a little bit more time, and then we're going to see the result. The first one finished. Now the second one finished, third one also finished. Let's close the processes window and go to counter.txt, and we see 30,000. That means our mutex is indeed protecting the critical section across different processes. One more thing I want to talk about before I finish this video is that if you have a choice between using mutex and using monitor or lock, so how can you choose between these techniques? I would say that if you want to use a lock to protect resources within a process, then always prefer either lock or a monitor over a mutex, because mutex is considered as a operating system wide resource. It actually takes more resource to create a mutex than to create a lock or a monitor. Unless you're trying to synchronize between different processes, don't use mutex. Prefer lock or monitor. And that's everything I want to cover in this video. If you have any questions, please let me know. If not, I will see you in the next one. In this video, let's talk about reader and writer lock. Reader and writer lock is yet another type of synchronization techniques to help with thread synchronization. We already talked about a regular lock, a monitor, a mutex. Why do we need a reader and writer lock? Let's talk about the reason behind that. A regular lock or monitor or mutex is always exclusive, which means that when a thread acquires a lock, only this particular thread has access to the shared resource within the critical section. However, in some cases, we want multiple threads read the shared resource at the same time, because reading doesn't cause any change. And when multiple threads are reading a shared resource at the same time, it wouldn't cause race conditions. And we use a regular lock, then the performance of the application will be hindered. So we look at this application, for example, we have a shared resource over here. So this is the shared resource, and the application is a multi-threading application, and we use different threads. So let's say this is a reader thread. I'm going to use R in the circle to represent a reader thread. Right? So it could be a reader thread, and there could be multiple reader threads because we just need to read resource at the same time and make decisions. So multiple threads working together, we can divide and conquer. So it would be a great idea to improve the performance with multiple reader threads. And there are other type of threads, which could be writer threads, which is responsible for writing to the shared resource. Writing includes making changes like deleting or update or add to the shared resource. Right? So I'm just using W to include all of those possibilities. And of course, there could be reader and writer threads. So the thread could be reading and writing at the same time. So if we have these kind of situations, then we shouldn't just use a regular lock or a monitor or a mutex, because we should allow all of these readers work at the same time. That's why we need a special type of lock, and that's what we call the reader and writer lock. So how does a reader and writer lock work? The reader and writer lock has to work in such a way that allows multiple readers to read the resource simultaneously. When one of the reader threads, for example, acquire the lock, other reader threads should be able to acquire the lock at the same time, right, so that they can work simultaneously. However, when any of the reader threads is holding on to the lock, the writer cannot actually do anything, right? So the lock is a shared lock between the readers, but it's an exclusive lock against the writers. Now, when a writer is holding a lock, then that lock is an absolute exclusive lock, which means any of the other threads, regardless of the types of the threads, cannot access the shared resource anymore. So this is the reader and writer lock. In reality, is there any possibilities that we use the reader and writer lock? Yes, we use them quite a lot. For example, in database systems, we have a database over here. Let's say this is Microsoft SQL Server. It doesn't really matter. Any type of database would have to implement similar mechanism for thread synchronization, because a server is hosted on a central place and multiple applications across the internet should be able to access the database at the same time. The request sent to the SQL Server, each request is always independent. So to the SQL Server itself, these requests generates concurrent access to the server. So therefore, if there is a database table that needs to be accessed by all of these different applications, and each one of them can be reading and writing, or just read or just write, or read and write at the same time, then similar type of locks, reader and writer lock, should be applied, right? And if you have worked with SQL Server before, you probably have heard of shared locks and exclusive locks. So when a select statement is executed, a shared lock is applied to a certain area of the table, right? So in SQL Server, the lock is more granular. There's rows you can lock, there's pages you can lock, there's different areas you can lock, right? So select statement would generate a shared lock, whereas a update statement or insert statement or delete statement will generate exclusive lock. So shared lock would be similar to the locks acquired by the readers, whereas the exclusive lock will be similar to the locks acquired by the writer. So this is a real world example where reader and writer lock needs to be used. Another example, it could be a web server, right? Let's say this is the web server, And the web server can be accessed by people from different places using their browsers. So let's say there are multiple users accessing the web server at the same time. So in order to improve the performance, the web server loads some configuration information into the memory and stored globally in the cache. Use this rectangle to represent the shared cache, right? So this is a shared cache, and each time when the user sends a request to the web server and the web server needs to access the shared cache, there could be a reading and could be a writing possibility. So when all of them have different possibilities, whether it's reading or writing, then we encounter the same situation as this one. Why? That's because in web server, usually when a request is sent to a web server, it's queued in the request queue, as we have implemented before, right? We have been simulating the web server with multi-threading programming. Although we just created a console application, but it's a very similar concept, right? So the requests are queued, and then the requests are distributed among different threads for handling the requests simultaneously. Because different requests could require reading or writing, therefore a similar type of lock needs to be in place. We need reader or writer lock to lock the shared resource, which is the shared cache. That will allow readers to read at the same time, but allow writers to gain exclusive access to the shared cache. This will guarantee the integrity of the shared resource. Same thing, this technique will guarantee the integrity of the data within the SQL Server database. So that's the theory. So now let's take a look at one example that is used for this particular scenario where we want to use a cache. And before we go into the code, I want to give some more information. So usually the configuration data could be stored in a file or could be stored in a database. Sometimes you may find that loading the configuration data from the database or from a file into a shared cache within the memory of the application, the web application, is a good idea. For example, if every request tends to access configuration data, then just load it into the memory. It would improve the performance a lot because it would decrease the number of round trips between the web server and the database, or from the web server to a file. Okay? You don't want to read and write all the time. Just put it into the cache and then eventually dump that cache into the file or back to the database. So it could be a good idea to load everything into the shared cache in this example, especially when there could be reading requests and there could be writing requests. Then in that case, we should apply the reader and writer lock. So let's take a look at examples where we don't apply the reader and writer lock first and see what potentially could happen. So let's jump into Visual Studio, close this and try to close this solution. And let's create a new project and let's call this, so still select console application and let's call this reader writer lock. So if I create a class here, I'm going to call it public class global cache, or call it global configuration cache, then the purpose here is to just cache the key value pairs in the dictionary. So I'm going to create a dictionary here with an integer as a key and a string as the value. So the cache would be like this, and we're going to instantiate the instance here. Now we have a add method here that allows us to enter the key and value. Okay, Visual Studio generated the code for me. And now for reading, we just use get and with the key, and here we just return it. So that's it. Quite simple. Maybe this could cause issues, so let's use a safer technique. So I'm going to say cache.try get value. So we try to get value of this particular key out for into the value variable, And if it's successful, then we're going to return this value variable, okay, as the result. Otherwise, maybe we'll just return null instead of empty. So then here we can use a question mark. All right, so this looks like it's going to work quite well for our purpose. And indeed, if you try this in your web application, you might be using it no problems. But once in a while, there could be weird errors in consistent state. Why this is happening? Well, it's just really because that these requests that comes from different users comes to the web server at the same time, that is handled by different threads from a .NET thread pool. Right? So because it's handled by different threads, they can be running in parallel, simultaneously running in different core of the CPU. Therefore, they might be accessing the dictionary at the same time. So there could be different threads reading and writing at the same time. And because the dictionary itself is not actually thread safe, right? We haven't talked about thread safety for data structures, but the easy way to understand this thread safety problem is that this particular operation looks like one line of code. This one also looks like one line of code. They're not really atomic. We talked about atomic operation before, right? So they're not really atomic. So if this is atomic, absolutely executed or not executed, then this implementation would have no problems. However, these are not atomic operations. So they are broken into different parts when the compiler compiles the code. So therefore, when multiple threads are running them, you might just run into inconsistent state against the dictionary, because the dictionary itself handles the state within the data struct. Therefore, when multiple threads are running at the same time and running with different parts of this operation, it just could really mess up the state of this particular dictionary. And eventually we're going to talk about concurrent data structures, right? And there is a particular one that is called concurrent dictionary. If we use concurrent dictionary, then we don't actually need to do anything. But if we use a regular dictionary, then we have to use locks to protect it. But we can't use a regular lock like this, right? We cannot use a lock like this. We cannot use a lock like this. Well, it's going to compile. It doesn't complain. However, your reader threads will not be able to access the cache at the same time. And if your web server is quite popular, a lot of users are using it, then you might run into performance issues. So what's recommended is the reader and writer lock. And the syntax is quite similar to the Mutex or the monitor. So let's try to use the reader and writer lock. So what we can do here is we can first of all declare a reader writer lock. It's better to use the slim version. So we create a new instance of this lock. And then when we are trying to do anything with it, let's say we're trying to add to it, we just say lock.enter write lock, because this is add. Okay? Add or update actually. So here it's doing add or update. Then in this case, we're entering into a write lock. So this is going to be the exclusive lock. And we don't need the curly braces. Let's delete them. And here, we're going to say finally, don't forget to exit. And then over here, we're going to do the same thing. So let's remove these code. And then we are going to say lock. And this time, we're going to say enter read lock. So this is going to be a shared lock between the readers. And then same thing here, we're going to put a try catch, and we're going to say finally read lock. So when we are using the reader and writer lock this way, then when the web application is using them, we're going to allow different reader threads to just access the cache simultaneously, whereas it's going to always block the writer lock. And when the writer lock gains access, it's going to block any of other threads. So there's only just one thing that we need to pay attention here. What if this throws exception before it successfully gain or acquire the lock? Right? So this throws exception without gaining or acquiring the lock, and then we still tries to exit the lock, then that could be potential issues. So for that, we can use a technique like this. So I'm going to say lock acquired equals false at the beginning, right? And if the line can be executed, so this line can be executed, that means we successfully acquired the lock. So we turn it into true. And then finally here, we are going to check whether the lock has been acquired or not. So I'm going to say if lock acquired, then we are going to exit the reader lock. So same technique can be applied here. Again, lock acquired, set to true over here. And if the lock is actually acquired, then we're going to exit the read lock. So this would be a thread safe global configuration cache that can be used within your web application that allows multiple readers and a unique writer in a given time. Okay, that's everything I want to cover in this video. If any questions, please let me know. If not, I will see you in the next one. In this video, let's learn about semaphore. Semaphore is another thread synchronization technique. However, it's less often used for protect critical sections. We have learned locks, monitors, mutexes, reader and writer lock. Those are all used to protect a critical section in order to avoid race conditions and inconsistent behaviors. Semaphore, although can be used to do the same thing, is more often used for controlling the number of concurrent threads or processes, because sometimes it is very important to limit the number of threads. So let's take an example which we have created ourselves, the web server simulation. And let's actually take a look at the diagram first. If you remember, we have a request queue here, and then we have a monitor that monitors request queue. And in turn, it generates different threads to process the request in the queue. So let me move this outside. So this is a processor, which is actually processor thread that is generated by monitor. And there can be multiple of them, depending on how many requests are in the queue at the current moment. Let's imagine that at one moment, there are thousands of requests that are queued into the web server. And if we are using the current logic here, you can see that this monitor queue task, which is executed by the monitoring thread, is in an infinite loop looking at the request queue. So if we have thousands of requests queued in the request queue, within a very short amount of time, there will be thousands of threads created in order to process the requests. So the request processor threads like this could be created to handle all of the requests in the queue. So all of these requests, all of the 1,000 requests, will be assigned by the monitor threads to be processed. And having thousands of threads running in the application can be too heavy for the server. That's why most of the web servers or database servers, they all have connection pools. And they try to limit the number of concurrent connections within connection pool. For example, the default concurrent connections that are allowed for Azure SQL Server database could be, I don't remember the exact number, but it's around 100 by default. So it's not that many. And if we are just using the code that we implemented to generate the process threads like this, then we are going to have too many threads running at the same time. And we don't want to do that. And semaphore is a synchronization technique that can help us to limit the number of concurrent threads or processes, because semaphore is like mutex. If you provide a name to it, then it will be system-wide. It can be accessed through different processes. Here is the basic syntax of using semaphore. So we're using the semaphore slim class instead of the semaphore class because semaphore slim is lighter than semaphore. So let's learn to use semaphore slim first. First of all, we're going to create an instance of the semaphore object by providing two parameters, the initial count and the maximum count. Usually you want the two numbers to be the same, so this limits the number of concurrent threads or concurrent processes for executing a specific section of your code. Okay, so if I say 3, for example, then the maximum number of concurrent threads or process can execute the protected section of code is 3. And then we call semaphore.wait. When we say semaphore.wait, we're trying to enter into the protected section. And as you can see, the protected section is right here. This doesn't have to be the critical section. We are just trying to limit the number of concurrent threads that can run this particular section of code. So when we say wait, we're trying to enter into it. If the current count is greater than 0, then we're able to execute this code. Once it finished calling the wait method, the current count will decrease by 1, decrement by 1. And then when everything is finished, we call semaphore.release. So this will increase the count. Okay, so how this works is, for example, if the initial count is 3, then if the first thread comes over and say semaphore.wait, it will see that the current count is 3. So it will be able to enter. But at the same time, it will decrease the current count to 2. And then very soon, the second thread comes over and also tries to enter by calling semaphore.wait. Then the current count decreases to 1. And when the third thread comes over, it will call semaphore.wait. Then the current count decreases to 0. However, the first thread, second thread, and the third thread, they all enter into the protected section. So they're able to execute the code within it. And when the fourth thread comes over, it sees that the current count is 0. Then it will be blocked right here on the semaphore.wait line, waiting for the semaphore to be released by the previous threads. Let's say at this moment, the first thread finished. Then the semaphore is increased. Right? Semaphore.release, this method increases the current count of the semaphore object. And because it increased the current count, the fourth thread, which is still waiting for enter into the protected section, will be able to just enter into the section right away. So that's how it works. Although I put all of these lines on the same screen, they don't actually have to be on the same screen. And actually, they don't even have to be in the same threads. Now, let's take a look at this example where we use the monitor thread here. I see this monitor queue is being called within a new thread. Right? And this thread is responsible to always monitor the request queue, and whenever there is a request, it will create a new thread. So in order to limit the number of threads, we can use semaphore slim class. So let's come over here and try to use that. I'm going to say using. We're using the using statement just because we want to make sure that semaphore slim object is always disposed, because it internally uses unmanaged resources, so we always want to get it disposed so that we don't have any memory leaking problems. So I'm going to say semaphore slim, and here we can say the initial count is just, let's use the same example, let's say 3. And then the maximum count is also 3. Now, when we have this, what we can do is at the place where we want to generate the thread, right? Just before that, we want to say semaphore.wait. So this allows us to protect the code right after it. Okay, so these code cannot be executed if the semaphore count is 0. Okay, so you can consider semaphore as a global counter. And we're using that counter to protect a session of code that can be executed concurrently. We're using that counter to make sure that only a certain number of concurrent execution of the protected session can exist at the same time. So we use semaphore.wait here to make sure this is protected. And the reason why we need to protect this is just because we don't want to generate too many threads here. All right, so we have the semaphore.wait. Then the question comes is, where do we try to release the semaphore? Well, here, once we gain the semaphore, right, the semaphore current count decreases, then we are creating a new thread. And we're doing our processing inside the thread. Once the processing finishes, that's when we want to release the semaphore, right? The purpose of gaining the semaphore is to do this processing. Therefore, we're released within the task of the thread. So here we're going to use try and finally, because we always want to release the semaphore. So we're going to say finally, and then we're going to say semaphore.release. I'm missing a curly brace here. Okay, so as you can see that we have the monitor queue method called within a thread, which is the monitoring thread. And the semaphore.wait is called within the monitor.queue. Whereas the semaphore.release is called within a different thread. Therefore, you can conclude that the semaphore.release and semaphore.wait, they don't have to exist in the same thread. So this comparing to Mutex or monitor or log or reader and writer log, they're different. All of the other techniques has something that is called thread affinity. Okay, so the thread who enters into the section will have to release it. In this case, semaphore, it doesn't implement thread affinity, therefore it can be called from different threads. In this case, exactly that scenario. All right, so with the semaphore.wait and semaphore.release here, and the initial count and maximum count set to 3, we're limiting the number of concurrent threads running at the same time. So what we can do here is we can inside here, after the release, we can say console.writeLine, and we can say that thread released semaphore previous count is this many. And here we're going to say thread.current thread.manage thread ID. And then here we're going to get the previous count. So the release method here actually returns the previous count of the semaphore. So we're going to say prev count equals this, and then we're going to put this into the curly braces here. All right, if we are running this, then you're going to see some interesting thing happening. All right, the application is running. And if I just type in, let's say I just type in A and enter. Now it says processed input A, and thread 12 released the semaphore. The previous count is 2. Why the previous count is 2 instead of 3? Well, that's because once thread 12 gained the semaphore, the count of the semaphore became 2. And after it released, we're asking to get the previous count. Of course, it's 2, right? And if I enter A and A continuously, then you can see that thread number 3 released the semaphore previous count is 1. And then 13 released the semaphore previous count is 2. That's because we continuously enter 2 letters. And there are 2 elements in the request queue, basically 2 requests in the request queue. And when the monitor thread, the monitoring thread over here tries to, not this one, over here tries to do the infinite loop, it sees that there are 2 requests, so it dequeued the first one and create the first worker thread. Then it dequeued the second one, it creates the second worker thread. When that happens, the semaphore.wait is called for each one of those threads. Therefore, when the first thread comes, the semaphore count became 2, and when the second worker thread came, the semaphore, after executing semaphore.wait, the semaphore count became 1. Therefore, when they release one by one, it will be saying 1 and 2. So if I enter A, all 3 different times, then it was showing you 0, 1, 2. Now, what's going to happen if I enter letter A or any letter 4 different times? Well, like I mentioned before, the first thread will have to be blocked, waiting for any of the threads to release the semaphore. So let's say I'm going to enter B, 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 B. It doesn't really matter what you enter. Now you can see that there are 2 threads finished processing and the previous count is all 0, right? So that means one of the threads released and then the 4th thread immediately entered, which means the previous count is 0. Well, this is the first thread that released, right? So, and then the 4th thread. So this is the 4th thread that immediately entered, and the previous count is, of course, became 0 again. Because after this, the count becomes 1, and then after this, the previous count becomes 0 again. So this is how it works. If we continuously enter many lines, you can see many previous count. This is basically all of them are being blocked, except that we only allow 3 different concurrent threads running at the same time. So this is going to slow down the processing. However, it's going to protect the application from overloading the server. So of course, I'm using 3 just for demonstration purpose. For your real world application, you might be considering like 50, 60, 70, 80, for example, or any number that fits your bill. So another thing before I finish this lecture is that, like I mentioned, semaphore can be a cross process. And for a semaphore to a cross process, you have to specify a name. So a named semaphore is global to the system. But you cannot use semaphore slim anymore because semaphore slim can be only used for local semaphore within a process. And you have to use the semaphore. So when you use semaphore, you can see there are different signatures. There's initial count, maximum count, and then the third parameter here is the name. If you need to use semaphore to protect a particular section across different processes, then you need to use the semaphore class instead of semaphore slim class. But if not, then just use semaphore slim. It does the same thing and it's not as heavy as the semaphore class. All right, let's recover back to use semaphore slim. And I just remember another thing that I want to emphasize is that here we're using semaphore slim to limit number of concurrent threads. But we have to remember that when we're doing this, we're not actually protecting the critical section here. In this example, the web server example, we have never used synchronization techniques to protect critical section. In fact, we should protect critical section, right? Because we're using a regular queue instead of the concurrent queue. We're going to talk about concurrent collections later. Here, because we're using a regular queue, then this DQ and this InQ, where is the InQ here? They become the critical section. So it's best practice to protect them because it's possible that we're inqueuing and dequeuing at the same time because they belong to different threads. Here, the inqueue is working within the main thread, whereas the dequeuing is working within separate worker thread. Using a simple lock here would be enough to solve this problem. We can do something like this. However, later we will be talking about concurrent collections. So let's make this work. Declaration is outside, and then the critical section is inside. And then we need to declare the lock from outside, and we can just say object and be called QLock equals new object, and then we're gonna lock our same thing here. We're gonna lock our QLock. All right. That's everything I want to cover in this video. If you have any questions, please let me know. If not, I will see you in the next one. In this video, we're going to talk about the AutoResetEvent, which is used for signaling between different threads. And the best way to describe it is to use the producer and consumer scenario, right? Because there has to be a signaling mechanism between the producer and consumer so that consumer knows whenever there is product produced by the producer. So let's use the farmer and pigs analogy to learn about this signaling mechanism. Let's say we have this farm where we have the farmer. This is the feeding station, and we have some animals. In this case, we have 3 little pigs. Whenever the farmer produces some food, the farmer will have to let the little pigs know that there's food in the feeding station. Come and consume, right? Come and eat. So the way to let the pigs know is to put out a sign in front of the feeding station. And because the pigs are waiting, so that once they see the signal, one of the pigs will go into the feeding station. And as soon as this little pig goes into the feeding station, the sign will be automatically taken away. So the other 2 pigs are like, okay, no sign, no food. So we're going to wait for the next one. And when this one finishes, this comes out in continuous wait. And when there's more food comes, the farmer will hand out the sign again. And this time, maybe this pig goes in, maybe still this pig goes in, maybe another pig goes in. There's not actually a pattern. One of the pigs will be able to get into the feeding station, and again, the sign will be taken away. When the little pig is eating in the feeding station, the farmer is still producing. Right? So it's possible that when the pig is still consuming, another portion of food is ready. So the sign is handing out again. So this little pig goes in, for example, then the sign is automatically taken away. And if the farmer is very efficient, then there's enough food produced for the 3rd time, and the sign is handing out again, and the 3rd little pig goes into the feeding station, also tries to consume the food, right? And the sign is taken away. So this is how the signaling works, right? So with this scenario, you have to understand the most important thing in the scenario, which is this signaling. It's a binary signal. It's whether on or off. When it's on, it's like handing out of the feeding station. When it's off, it's automatically taken away. And this is one thread, which is the producer thread, and these are the consumer thread. Of course, it doesn't have to be just one producer, but let's use the example of one producer thread and multiple consumer threads. And the signaling works this way, that whenever there is a product produced, the signal, remember this is a binary signal and there's only one signal, right? The signal will be turned on, and the consumer who's waiting will be able to consume the product. And once one of the threads starts consuming the product, the sign will be turned off. And whenever there's more product produced, the sign is on again, and a thread will be able to consume. So this binary sign, which is a single binary sign, has only 2 states, signal state or non-signal state. And whenever the sign is in signal state, one of the threads that are waiting will be able to proceed. If it's off, then the threads will have to be waiting. So let's jump into Visual Studio and see how this works in action. Let's go to Visual Studio and create a new project. And this time we're going to call it Signaling AutoResetEvent. All right. So over here, first of all, what is the basic syntax of using the AutoResetEvent? You're going to declare the AutoResetEvent just like you declare any other variable, right? Create an instance of this. There's one parameter here and you have to pay attention. This one is the initial state. So when the program starts running, do you want the sign to be turned on already, or do you want it to be turned off? Usually at the beginning of the program, I want it to be turned off because I don't have any food. But some programs already have food when the program starts running. Depending on your situation, you want it to be false or true. If you have product already to be consumed, then use true, otherwise use false. Right? And this AutoResetEvent also has some unmanaged resources, so it's better to use the using statement at the front so that it's always disposed when the program exits. Now, for the consumer thread, right, the consumer thread will be calling AutoResetEvent.wait. It's not called wait, it's called wait1. So I'm waiting for one of the product. You can sort of understand it this way. So wait 1. The producer thread will be saying, okay, I'm ready. I have some food for you or some product for you. Go and get it. So it's simple, right? So you declare the object and then you wait and you set it to send the signal. So when you say set, you turn on the signal. And once the consumer starts consuming it, the signal is automatically turned off. So that's how it works. Okay, so let's say that we're going to have a main thread and a worker thread. The main thread is responsible to provide a signal for the consumer thread to either proceed or wait, right? So it's like a traffic cop, right? The main threads are like a traffic cop, and the worker thread is like the train that's waiting for the signal. Okay, so let's remove this, and we're going to use the AutoResetEvent just like this. And we're going to have a user input. Okay, so this is the signal that the user provides. And we're going to use console.write to signal to just provide some information. So server is running type go to proceed. That's it. Now the main thread receives user input and sends signals. Okay, so we're going to have an infinite loop here, and it's waiting for the user to enter something. So we're going to say user input equals to console.read line. And now we're going to signal the worker thread. Signal the worker thread if the input is go. Okay, so if the user input equals, let's do it to lower. So if this equals go, then we're going to signal the worker thread. I'm going to say AutoResetEvent set. Okay, so signals the worker thread to proceed. Now the task for that worker thread, so let's create the task first. So the worker thread is going to do some work here. And again, the worker thread is going to be an infinite loop waiting for the go signal. So I'm going to say console.writeLine, and I'm going to say worker thread is waiting for the signal. Okay, and then the worker thread is going to say, I'm going to come here and wait. I want to have a signal. Once it comes over here, the program blocks, right? Blocks and waiting. So once it actually receives the signal, it's going to proceed to the next line, which is line 28 here. I'm going to say worker thread proceeds. And then I'm going to say thread.sleep for maybe 2 seconds. This is to simulate a processing time. The worker thread proceeds to do some work, which takes 2 seconds. And then when the user, so here's a green screen line. Maybe I'm just going to do this to remove it. Okay. And then when the user provides another go signal, then the worker thread is going to again proceed to do some work. And after 2 seconds, is going to come back and wait for another signal. Right? So this is going to be an infinite thing that goes on and on. And before we run it, actually, we need to start the worker thread before the while loop. So here I'm going to say start the worker thread, and I'm going to say worker thread equals new thread. And what kind of work does it do? It does its worker work. So just like this, and then we're saying worker thread now start. All right, let's go ahead and run it. Okay, it says server is running type go to proceed. And then it says worker thread is waiting. So our worker thread is currently waiting. It's like a train is waiting for traffic cop to say go. So I'm going to type in go as the traffic cop, and then I hit enter. And then it says worker thread proceeds. 2 seconds later, it says worker thread is waiting for the signal again. Right? And then you can do this. You can do go and worker thread now proceeds. And now worker thread is waiting for the signal again. You can see how this works, right? As soon as the worker thread says wait, it's just waiting for that binary signal to be turned on. And as soon as you turn it on by saying AutoResetEvent.set, it basically turns on the binary signal. And once it's turned on, one of the worker threads, in this case, when you have one worker thread that is waiting, it will proceed. And as soon as it proceeds, the binary signal is turned off, right? So if we have multiple worker threads waiting for doing the work, then because it's turned off, only one worker thread can proceed. Only one worker thread can proceed. The other ones will be still waiting, just because once one of the worker threads proceeds, the signal is turned off again, right? So we can try to do multiple worker threads. So for that, instead of using just one thread, we can use a loop to create multiple worker thread. And instead of 10, I'm going to use just 3 worker thread here. And we are going to say thread dot thread worker thread equals new thread. And again, it's going to do the same type of work. And I'm going to provide a name to the worker thread. And I'm going to say worker I plus 1. Okay. And then worker thread dot start. I'm going to start all of the thread. And here in the main thread, it's going to do the same thing. Just main thread provides the go signal. And in the worker thread here, I want to provide more information. So I'm going to use string interpolation again. So worker, so I'm going to remove this. And here, I'm just going to say thread dot current thread dot name. Okay. And I'm going to do the same thing for this one. So that we know which thread is actually proceeding. So this one proceeds. Okay. Add a dot at the end. Now we can run this again, and this time we have 3 different worker threads waiting for the signal. So this is like the 3 little pigs waiting for the food. Let me turn off this so that the new one can be running. Okay, so we have worker 1 waiting, 2 waiting, 3 waiting. And then I type go, worker 1 proceeds. And then once worker 1 finishes, it's waiting for the signal again, right? And if I do 2 continuously, you can see that worker 2 proceeds, worker 3 proceeds, and then each one of them finishes and waiting for the signal again. If I enter go 3 different times, right? So worker 1, 2, and 3 proceeds. You can see that there's no particular pattern who's going to get the food, right? And of course, our program in this case has flaws. Not all of the food can be consumed, which you can try to fix that with a queue. Right? Because if I enter this for like more times, and if I increase the wait time over here, there could be more food produced and more signals provided, right? So this could be set for 10 times, and only 3 of them might get the signal. Because once one of the threads proceeds, the signal will be turned off no matter how many times you have set it. In order to not lose the product, you need to put the product in a queue, which is very similar to the web server scenario that we created, right? We put everything in the queue. And then our monitor thread is like the producer, right? And the other threads are like the consumer threads. And that's everything I want to cover for the AutoResetEvent. Again, I want to emphasize that you can see that we're not using the AutoResetEvent to protect a critical section. We're using it to send signal between different threads, right? So this is for threads interaction purpose instead of shared resources. However, it's all related. We want to send a signal for the purpose of consuming the shared resource. In this case, the shared resource is the signal go. Although we don't have to get the signal from the worker thread, but most of the case you want to get the data, which is the product. Anyway, this is everything I want to cover in this video. If you have any questions, please let me know. If not, I will see you in the next one. In this video, we're going to talk about signaling with ManualResetEvent. ManualResetEvent is similar to AutoResetEvent, except that the reset is not automatic. So what do I mean by reset? Let's go back to the AutoResetEvent here. once the pig go into the station, the feeding station, to eat, remember the signal here is automatically turned off. The turning off of the signal is called reset. Turning on of the signal is called set. The auto reset event just means that when the waiting thread perceives the signal is turned off automatically without the developer manually turning it off. Whereas in the manual reset event, the developer is responsible to call the method reset in order to turn off the binary signal. It's still a signal with an on and off, two different modes, but you will have to turn it on manually. You will have to turn it off manually as well. So where are the scenarios in real life that we need such mechanism of signaling? Let's still use this farm analogy here. Previously, we were saying that only one pig can go into the feeding station, but that's not realistic, right? Realistically, the farmer produces food in batches. It produces a lot of food and probably more than enough for 3 little pigs to go into the feeding station and eat at the same time. So in that case, we should allow multiple consumers to consume the products at the same time. And some other examples I can think of is, for example, really like traffic light. If we are thinking that each vehicle has threads and the traffic light will be the signal, once it turns green, everybody will go at the same time, right? Everybody goes until it turns red again. So it's not one car at a time. Other scenarios I can think of is, for example, a file is produced and the file is huge and you need separate threads to divide and conquer at the same time. Therefore, you will signal those threads to say, go ahead, divide the file and conquer it. And once the file is finished, then we can signal the producer again to say, hey, the file is finished, go ahead and produce more. This is where we use ManualResetEvent. And the syntax is pretty similar to AutoResetEvent. Still here, we're going to say ManualResetEvent, and then the variable name, let's just call it ManualResetEvent, and we're going to create this. And this is the initial state. For ManualResetEvent, there is actually a slim version, so I would encourage you to use the slim version instead of the original version. And here, again, you can use the using statement to make sure that the ManualResetEvent object is automatically disposed after the program exit. And then at the place where you want to turn on the signal, you call the set method, just like the AutoResetEvent. And then at the place, whoever is responsible to turn it off will have to call the reset method to turn it off. So that's the basic syntax. So let's create a very simple application here where, let's say, 3 different worker threads are waiting for a signal to proceed. They're all blocked at the beginning until a signal is provided from the main thread. So I'm going to say for, and then use a for loop to create 3 different threads here, and say thread equals new thread, and it's going to do some work. So I'm going to do this work, which I will create later. And then thread name equals thread I. It to be either thread 1, thread 2, or thread 3. And then I'm going to say thread.start, start the thread. Now, in the main thread, we are going to output some message first. So I'm going to say press enter to release all threads, right? Because all of the threads are being blocked at the beginning because the initial state is false. And then we're going to say console.readLine to wait for the user to press enter. And at this moment, the main thread is going to set the signal, turn on the signal to release. Okay, so after the user press read line, the main thread is going to signal the worker threads to proceed. And then at the very end, we're going to say read line again, just so that we don't automatically exit out. And then over here, we're going to define the work method here. And we can just provide some messages with saying which thread.currentThread.name is waiting for the signal. And then here we use the wait method. So this is the slim version, so it has a wait method. This wait for the signals. So once it receives the signal, then it can process the products that the producer produces. In this case, the producer is the main thread, which produces this enter keystroke. Here we can use thread.sleep just to simulate a longer process time. And then here we're going to say red line, and then we can say whoever over here released. All right, so this is a simple program. Although we don't have a reset over here, we don't need to do a reset in this simple example, but it demonstrates that multiple threads be released at the same time. So let's run this. And then you can see that thread 1, 2, 3 are waiting, and press enter to release all of the threads. So this message is in between, and then I don't like that. So maybe we can move this console.write to the top. This will fix this particular issue. Let's run it again. So press enter to release all of the threads, and it tells you that all of the 3 threads are waiting. It's like all of the 3 little pigs are waiting for the food. Now, if I just hit enter, you can see that after a brief moment, the threads are released. So this is how the ManualResetEvent works. Because it is not reset automatically, therefore all of the threads are allowed to enter. The reason why the AutoResetEvent only allows one thread to enter is really just because it automatically resets it as soon as it receives the signal. Right. As soon as one thread receives the signal is turned off, so no other thread will be able to receive the signal anymore. Here, because the reset has to be called manually, therefore all of the threads has an opportunity to enter, right, to pass this wait line. So this is how it works, and then in the next video, we're gonna actually practice a little bit using the ManualResetEvent in the next one. This video is going to be your third assignment, and in this video, we are going to use ManualResetEvent Slim class to create a two-way signaling in the producer and consumer scenario. So first of all, let's talk about it. We're going to use this farmer and pigs analogy again. The farmer represents the producer, and the pigs represents 3 different threads who want to consume product. So the farmer here will produce batch of food. Okay? And once the batch is ready, the producer is going to signal the worker threads. And all of the worker threads will be able to jump into in this case, the feeding station. And when you create it, what you can do is you can use a queue. And every time you produce, let's say 10 numbers, and just put the numbers in the queue. And then the producer will have to signal the worker threads to consume numbers in the queue. So it's like a divide and conquer scenario, right? Let them all in, divide the queue, and conquer it. And once all of the threads finish, which means the queue is empty, then they will have to send a signal back to the producer and say, hey, the queue is empty, we're still hungry, you can now produce again. Now, if the farmer wants to do it, then the farmer can produce another batch. So what I want you to do is, I want you to use the main thread to represent the producer. And then you can use 3 different worker threads to represent these 3 little pigs. And then you create a queue every time when the user press maybe letter P, for example, then it's going to start producing 10 different numbers or whatever, maybe 20 different numbers, maybe 100 numbers. Doesn't matter how many numbers. You put it in the queue, and then you send a signal using the ManualResetEvent to the pigs. And once the pig all finished the queue, then you send a signal back to the farmer and say, hey, you now need to produce, and of course a message will be on the screen saying press P. Only when the queue is empty do we want to see the message. And then we of course, as the user, you will press on the P, and then another 10 will be produced as a batch and enqueued into the queue. Now the pigs are ready to produce again because they signaled again. So this is going to be in the infinite loop. So you can produce and produce, go on and on, just like life. That's the requirement of this assignment. Again, the queue is going to be a regular queue. Don't worry about whether it's safe or not. If you want, you can use a lock to protect the queue. But for now, you can assume that the queue is thread safe. Just do whatever you want with it. You don't have to protect it as a critical section. We're going to talk about concurrent queue in the future. So don't worry about the thread safety about the queue. I'm going to briefly talk about thread safety about the queue again in the next video. Okay, try to go ahead and work on that yourself, and I will see you in the next video. Now let's work on this assignment, two-way signaling in producer and consumer scenario. Let's jump into Visual Studio right away. First of all, we will need to focus on the producer, which is the main thread, as I mentioned in the requirement. We're going to have a while loop, and then inside the loop, we are going to produce. So first of all, we're going to have a write line, and I'm going to say, in order to produce, enter letter P. And then we're going to read the input from the console, just like this. And if it's null for whatever reason, use empty string. And here we're going to use the if statement. So if the input, maybe do a 2 lower, just like before. So 2 lower, and if the input is letter P, then what are we going to do? We are going to produce a batch of food. Remember? I'm going to say from 1 to 10. Let's say each batch has only 10 items, just so that we can debug, right? We don't want to see like thousands of items on the screen. And then we're going to say queue.enqueue. So here we need to declare a queue. This represents the feeding station in the farmer and pigs scenario. So we're going to have a queue. We can use a regular queue, and it's going to be a queue of number. And then I'm going to say queue equals new queue. Looks like this collection is not being used, so I'm going to do a control dot to just remove unnecessary using statements. So here I'm going to do a enqueue. So I'm going to just enqueue I, and then I'm providing a message here. I have produced I. So once this finishes, I want to signal the worker threads that I've produced a batch and go ahead and consume it. So because of that, we need to declare a event. That's going to be a manual event. So I'm going to say ManualResetEvent slim, and I'm going to call this consume event. And the initial state is false. Right? It's only turned true, right? Turned on when this is ready, right? When the batch is ready. So we do the set. Now we come back and focus on the worker threads. So come back over here, maybe just above this. Well, we had to do it above this, right? Because this is the main thread, and this is going to be blocking because it's a well infinite loop. Okay, so here we're going to have a array of consumer threads. So I'm going to say 3, okay? And I'm going to have a for loop that produces those 3 different threads. So from 0 to 3, to 2, and I++. And over here, I'm going to say consumer threads, I equals new thread. And the work that the thread is going to do is going to be called consume, which I haven't created, but I'm going to write it here. So consumer I to start. Before I start it, I want to give it a name, just so that when I output, I can see the name. So dot name equals consumer, and which consumer? It is the consumer I. All right, now I'm going to have a comment, so this is producer. Now we're going to define the consumer's behavior. So void and then consume. So this is the task that the consumer is going to perform. So again, this consumer is going to do a while loop as well, so that it just does not exit. And when you produce another batch, they're ready to work on it again. Here, we're going to use the consume event, right? Because we need to be blocked if it's not signaled yet, if the batch is not ready. So only when the batch is ready, which is starting from line 40, do I need to take a look at the queue, right? So I'm going to say, well, and then I'm going to say queue.try, and so out var input, I'm not going to use this automatically generated code. I'm going to say int item. So I know it's integer, so I'm going to use its integer. Okay, so here within this while loop, this is where the work is, right? So work on the items produced. I don't want to just dequeue one of them. I want to keep getting it if it's available for me. Okay, so I'm going to say thread.sleep. Maybe sleep for maybe half a second. So I'm going to say console.writeLine, and then this is announcing to the world that I'm consuming, so not consuming, I'm consumed. I have consumed which item? This item from which thread? From myself. So I say thread.currentThread.name. Now, as I mentioned, if you worry about this thread safety of the queue object, it's because it's a regular queue that you can use a lock to protect the in queue and the dequeue. For now, we're not going to worry too much about it. If this is a real world scenario, of course, I encourage you to protect it, a lock. However, in the real world scenario, you wouldn't use a regular queue. You can use the concurrent queue. We're going to talk about that later, as I mentioned. Now, the problem is that how does the producer know that the consumers have finished consuming all of the items in the queue, right? All of the food in the food station. There has to be a signal from the consumer to the producer. So right now, we already have a consume event. So this is used to signal from the producer to the consumer, so that the consumers can go ahead and consume whatever that is in the queue. Right now, the queue is empty. When the queue is empty, the consumer needs to send a signal back to the producer. And for that purpose, we need to create a second. So let's copy this and just paste it. And here, we're going to say, instead of consume event, I'm going to say produce event. And we're going to turn this on at the beginning. What does this mean? So initial state is true. When the initial state is true, that means we allow whoever is waiting to enter directly. So that means the producer, if the producer is waiting, then the producer can directly go ahead and produce. That's the initial state. If we don't have this to true and apply a wait here, right? So let's say I'm gonna apply a wait here, produce event, and I'm gonna just say wait. Then if this is false, then the program will just stay there. This is gonna be blocked, and it's gonna be blocked forever, and that's not right. At the beginning, we have to say true in order to let the program go to the next line. What we can do here, we can say produce the event, and then we can say reset. Reset means we're going to turn it off, because I already produced. I don't want to produce again until the queue is empty. That's why we have a reset. And what this means is that once all of this finishes and come back to the while loop, right, because it's while true, so it's going to come here and execute this, and it's going to be blocked because this line has already been executed once. So here it's going to be blocking. Then the consumer has the responsibility to tell the producer that when the queue is empty. The problem is how? How does the consumer know the queue is empty? We might think it's easy because when the code execute over here, it just means that the queue is already empty. Otherwise, it's going to be in the while loop. It's always going to consume all of the items in the queue before it comes over here. So over here, we can just say produce event dot set. Right? Once we set it, it just means that the signal is on. And at that moment, if the main thread is being blocked over here, it's going to just come over here, right? And it says to produce, enter P, and then it's going to be blocked again on the IO on line 22. So at that moment, if the user press P and hit enter, then the whole thing happens again. However, there could be a problem in here because remember we have three different threads. Three different threads represents three little pigs, and each one may execute this, which may cause overproducing, right? Overproduction, and we don't want to do that. So in order to avoid that, we can create a counter. So maybe come over here at the top. We can have a consumer count set to 0. So, and then over here at the end, we can say consume event, not consume event. We can say consumer count increment by 1. And then if the consumer count equals to 3, that means that all of the three little pigs, right, all of the three worker threads have already finished this while loop. That means that the queue is empty, and only when the consumer count equals to 3 do we set it. So we can move this into if statement here, and then we can set it to 0. And now we can console on the right line. We can say, just make it clearer, have this, and then we can say something over here in the middle. We can say that more please, okay, more food please. And then here, some more stars. Okay, this seems to be right. However, there's a couple of more things we need to talk about. Right, so we use the produce event.set to signal back. We use the reset in the main thread here to turn the signal off. So we have this consume event, which we never call reset to turn it off. Remember, it's a menu event, so we have to turn it off. So where do we turn it off? Right, we can't turn it off right here. So let's go up here. And producer here, you can see that we directly turn it off. Well, that's just because we have only one producer. Here, you can't say consume event and reset. If you do it this way, there could be only one consumer, only one worker thread working for this entire application. And we don't want to do that. We want to utilize the multiple threads. And therefore, we think that here could be a good place, right? So when I say consume event, not uppercase, I'm going to say consume event, and I'm going to say reset. So here we are turning off the signal so that no other threads can enter anymore. And this allows the producer to signal it again. So if we don't do the reset, then the signal is always on. So that doesn't make sense. So we have to call the reset to turn it off, allowing the producer to have enough time to produce a batch. And then here, the consumer, one of the consumer, signals back to the producer and saying, give me more, right? Now, the second thing I want to mention is because this is multi-threading, right? The consume is a task that is performed by three different threads. Therefore, this line, they are considered critical section, right? So we need to use a lock to protect it. So let's go up here and let's create a lock. So I'm gonna say lock object, or maybe say lock consumer count, which makes more sense, equals new object, and then come back over here. And we have to protect, so lock like that, and then are going to move all of that to in between. All right, so that's the implementation. Let's run the program and see whether it works or not. Let me increase the font, and if I say P and hit enter, you can say produced 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it consumed 3 from thread 1. So thread 1 consumed 3. Thread 0, why it says thread 0? So let's fix that problem. So it's from 0 to 2, therefore this has to be increased by 1. Okay, let's try it again. Let's increase the font, press P. All right, so thread 2 consumed 1, thread 1 consumed 2, and you can see that all of the 3 different threads are involved, and they consumed 1, 2, 3, 4, 5, 6, 7, 8, 9. What about 10? Oh, here, 10 is here. Right, consumer 3 consumed 10, and then one of the thread, I think this is the consumer 2, reached the consumer count equals to 3 scenario. Therefore, it says more please, and then it gives the signal and say to produce, enter P. So when it comes to here, that means that our main thread has been waiting over here, and because thread number 2 gives the signal, therefore it comes to this line and currently blocked on here. Now here, if I do P again, you can see that 10 different numbers are produced, and then the consumption begins by 3 different threads, and this consumption is different. You can see this is consumer number 2 starts first, and this is consumer number 3 starts first, and it consumed number 3. Right, so this one consumer number 2 start first, and consumer number 1. So it's random. Right? There's no pattern. And over here again, more please. So it signal back to the main thread and says, give me more. Now I am the producer. I have the power to produce or not, or maybe just keep them hungry for a little bit. And after some time, I think it's ready. Then I press P and hit enter. Now another batch is produced. So this is the implementation. And in this implementation, we learned about using 2 different events to have two-way signaling between producer and consumer. And we learned about using the reset method to turn off the signal when we need to turn it off. Okay, that's everything I want to cover in this video. If you have any questions, please let me know. If not, I will see you in the next one. In this video, let's learn about thread affinity. We have talked about thread affinity when we talk about semaphore and locks and monitor. At that time, we were saying that any lock that is acquired by a thread has to be released by the same thread. That is thread affinity. Whereas semaphore doesn't have a thread affinity concept. So a thread can acquire the semaphore and another thread can release it. But thread affinity concept is not limited to thread synchronization. Any resources that are used within a thread usually have thread affinity, which means that only the thread itself can access those resources. For example, we have this application is a Windows Form application for demonstrating offloading long-running tasks. And we created 2 buttons to show different messages on a label. So these are the 2 buttons, and we're showing the message on the label. Right? So if we go to the code behind, or the CS file here, we have the event handler. However, we created 2 separate threads, and each thread is calling this. This has been working for our example. But if we set a breakpoint over here, if we run it in debug mode, we will see some exceptions. So let's run it and you will see exactly what I mean here. So click on the message 1 button and just wait for 3 seconds, I believe. Okay, so now you can see the message is first message, and if I just press on F10 to continue, immediately you see this cross-thread operation not valid message here. Okay? And it says control label message accessed from a thread other than the thread it was created. See, this is thread affinity, which means that the label is created within the main thread, right, the UI thread. However, here is a function that is used within different thread. It's a background worker thread that is triggering this, and it's the background worker thread is trying to access a resource that is created within the main thread. And that's why it's complaining. Right? It cannot be like that. Why it was working at runtime? Right? So if I just run it without debug, it will be working. Why it's working at runtime? Actually, I'm not too sure. I have been expecting the exception even at runtime. I think my assumption at runtime is that the Windows Form kind of like the framework hides that type of exception on purpose, although I didn't find any documentation about this. So this is thread affinity problem. So in order to still access this label from a different thread, we need to use something that is called invoke. By calling the invoke method on the control, which is in this case the label, it kind of synchronizes context. Okay, so what I mean by that is that we have different contexts here. We have a thread, which is a different threads than the main UI thread that owns this label. We need to kind of make these two threads become one when we try to access the label from a worker thread. So that's what I mean by synchronization context. So we need to do something like this. LBL message dot invoke, and then here you can see that it takes an action. For that, we can use a lambda expression, right? And within that, we can move this message over by Alt and then use the arrow to move it and format it. So if we do it this way, then there will be no problem anymore. Because if we recall the delegate through the invoke method, we're basically calling the delegate within the thread that the label was created in. I set a breakpoint and if I run it, now if I click on message 1 and just wait for 3 seconds, then I'm going to do F10 and you can see that it passes through without any problems coming back. You can see first message, right? So using the invoke method basically synchronizes the context between the two threads. And you can see that the documentation says that execute the specified delegate on the thread that owns the controls underlining window handle. Right? It basically just synchronizes, right? Just like what I mentioned. Another thing I want to point out is that it's better to use something like this. So if I go to label dot, and you can see that I have this invoke required. So this is a boolean. What you can do is that you can check whether invoke is required or not. Right? So if the invoke is required, then you can do you can use the invoke method. Otherwise, you don't have to. Right? So this takes the guesswork away. You don't have to always be aware whether the invoke method needs to be used or not. You can just do this and it will work for all the cases. If this show message is called within the UI thread, then this will be executed instead of using the invoke method. So you can do this and still it's going to work for you. No problem. I can do message 1. It's not going to throw me any exception. I'm going to do message 2 and it's going to work as well after 5 seconds. See the change to message 2. All right, so this is an example with Windows Form application. I want to give you another example, which is in Espionage Core Blazor. I know it could be a slightly complicated concept, but it's going to help you to understand that the thread affinity is everywhere. So I'm going to create a Blazor web application. I'm going to say Blazor thread affinity, and then interactive mode, I select the server interactive mode. Interactivity location, just keep it as global or just select global if it's different. And then click on create. You don't have to worry about what this means. I'm just creating a simple scenario so that I can demonstrate that to you. So this is a web application, right? And then I can go to components and go under pages. Here I can go to home. So this is the home page. I want to add something to the home page. First of all, I want to add 2 line break, and then I'm going to create a button. So the type of the button is button, and then get to a different line. And then over here, I'm going to say that the class is button and button primary. So this is from Bootstrap. I'm going to just make the button look better. And then after that, I'm going to react to the click event by saying @onClick. And here is a delegate, and I'm just say display time. So the caption of the button, I'm just going to say display time. Now the display time should be a delegate which needs to be created. I'm going to create a code block over here, and then I'm going to go ahead and create the display time method here. Once I do that, you can see the rescue line is gone. So I can go ahead and implement this display time functionality here. So what I can do is I have to display the time somewhere. And for that, I'm going to declare a variable to store the current time. So I'm going to say current time, and I'm going to initialize that to empty string. And when I click on the display time button, the current time needs to be assigned a time.now.toString, and that's it. Right, so if I do it this way and run it, if I click on the display time button, nothing is happening. Well, that's because we didn't do anything here. We did have this current time, but it's not displayed anywhere. So what I can do is I can have another 2 line breaks, and then over here, I'm just display my current time. Oh, this is going to display the current time just above the button. And then I'm going to do how reload doesn't work for me. I know that, so I'm going to just restart the application. Coming back to this, click on the display time. So immediately you can see the time displayed right here, right? And there's no problem with this. However, if I use a different thread for this, then you're going to see problems. So let's create a different thread. I'm going to say thread equals new thread. And we need to provide a task to it. And to simplify this, I'm going to just use lambda expression to have that. And we are going to say, we're going to move this into it, right? And then if I do it this way, nothing is going to happen actually. I want to show this to you. Let me add a little bit delay. Thread.sleep. We're going to sleep for half a second. And let's run it again. All right, we're going to click on display time and see nothing is happening. Well, that's just because we're using a separate thread and the UI rendering has already finished before this line is executed. Therefore, we need to do something special here. We need to say state has changed. Okay, so this is from the base class. You can see component base. So this, when I say state has changed, it will trigger the UI, which is the web page, to re-render, right? And this will help us to display this current time. We'll kind of refresh the current time on the page. However, at this point, we're going to run into thread affinity problem. So let's restart the application. Okay, and click on display time. Nothing is going on. And not only that, you can see that it says attempt to reconnect. So this means that something is happening. So if you go to F12, you can see all kinds of errors. So this is the developer tool in case you haven't worked with web application. Pressing F12 will bring up this tool, which is called the developer tool. And then under the console, you can see the error messages. It has all kinds of errors, but it doesn't really tell you what is going on here. This is really just because we're running into the thread affinity issue. So what this issue is really is that we are trying to call this state has changed method, which tries to re-render the UI. However, the UI should be re-rendered through the main thread. So there is this problem, the conflict. So same solution, you have to synchronize the 2 threads context. So in order to do that, we use the same thing, the invoke method. We're going to say base.invoke async. And then this will also take an action, which is a delegate. So we can just call this state has changed method within the invoke method. And this will solve the problem because this just kind of synchronized the 2 threads context as one. Run the application again, come back and click on display time. And now you can see that we have this new time. Now wait for a little bit and click on it again, and you can see the time refreshes. By showing you these 2 examples, you can see that we have this thread affinity issue, and we have to pay attention that we only access the resources that are created within the thread in itself. You cannot access it from a different thread unless you use the invoke method to synchronize the different contexts. And we're going to come back to thread affinity when we talk about async and the await keyword later in the course. Okay, that's everything I want to talk about in this video. If you have any questions, please let me know. If not, I will see you in the next one. In this video, let's briefly talk about thread safety. We actually have been talking about thread safety all along during the synchronization section. But I just want to mention this concept because you will see that in the documentation or in the blog, people are saying that this is thread safe, that is thread unsafe. You need to know by this point what they are talking about when they say something is thread safe. So in multi-threading computer programming, a function or a data struct or a class is thread safe when it can be used concurrently by multiple threads without causing race conditions, unexpected behaviors, or data corruptions. So, which means that within the function or the data struct or the class, proper locking mechanisms have already been used. For example, we were using a regular queue in the producer and consumer example. When we use a regular queue, there's going to be a problem, which I mentioned, right? So because the queue itself is not thread safe, what it means is that when multiple threads are using this instantiated variable, data within the queue can be corrupted. The behavior or the end result can be unexpected. Right? It depends on which thread get to it first, which thread get it later, and therefore you're going to see unexpected behavior. Sometimes it turned out to be wrong in one way, sometimes it turned out to be wrong in a different way. It's really just because the class queue does not internally use any thread synchronization techniques like locks, Mutex, semaphore to make the shared resource within it thread safe. That's what we call thread safety. Next time when you see a documentation it says something is thread safe, you know what it actually means. And just remember one thing, something is thread safe, it's because it can be used within multiple threads concurrently without causing any problems. Alright, that's everything I want to talk about in this video. If you have any questions, please let me know. If not, I will see you in the next one. In this video, let's talk about deadlocks. Deadlocking situation usually happens within threads that have nested locks. So basically, let's take two thread example. Let's say this is the first thread and this is the second thread. So when both threads are trying to wait for each other, okay, so thread 1 waits for thread 2 waits for thread 1, then they get into a deadlock situation, no one can proceed. Let's jump into Visual Studio and see an example. Let's close the current solution and try to create a new one. Let's create a console application and let's call this deadlock example and click on the create button. Now let's imagine we're working with a e-commerce system, right? So where we have users and we have orders. So depending on which functionality you're looking at, sometimes you're managing users, sometimes you're managing orders. So let's say we could be managing users and another one is managing orders. And managing users could mean that we're managing an order within a user, right? So this would go from user to order. And managing a order could sometimes mean that we're managing a user within the order. So the other way. And because of this, we might run into a complicated resource management when we want to get consistent behaviors by using multi-threading programming. So in that case, one thread, right? So for example, thread 1 wants to lock the user object first. Lock user first and then lock the order. Now thread 2 wants to lock the order object first and then lock the user. So let's have some code going. So we might have a function that is called manage order or manage user first, for example. And in here, we're going to have a lock. So here, because we're managing users, we lock the user lock first. We don't have the user lock declared yet, but let's continue writing so that we don't break our flow of thoughts. We lock the user lock first, and then let's just console write line, and we say user management acquired the user lock, and do a thread sleep. And let's sleep for, let's say, a second. So this is to simulate the work takes some time. And then internally, once it finishes doing something with the user, it wants to continue to do something with the order. So it needs to order object. So I'm going to do a order lock. And here, we're going to just console.write line. And I'm going to say user management acquired. The typo here, let me remove one of the C's. So acquired order lock. Right? And now we're going to have the reverse, which is the order. Let me just copy and paste and just change a few words. So instead of manage user, we're going to change this to manage order. And first, it wants to acquire order lock first. Right? And then here, we're going to say order management acquired the order lock. And now inside it, once we process the order, we want to process the user within the lock. So we lock the user secondly. And here we're saying the order management acquired the user lock. And let's say that the user, manage user, this manage user functionality takes longer time. Let's say 2 seconds. And manage order takes shorter time, which is 1 second. And let's just declare those locks. So object, user lock, new object, and order lock equals new object. All right, now let's create a thread. So we'll have a new thread, and what this new thread does is to manage order, because I'm going to call manage user within the main thread. I'm calling this function directly within the main thread. Now 2 threads are going. Right? One is the worker thread, the other one is the main thread. And I'm going to say thread.join. So let's wait till it finish. And let's do a console.read line. And then here we're going to say console.write line. The program finished. And now let's run the application. Okay. So now you see this 2 line, but you don't see program finished. Press any key to exit. Why is that? Well, let's look at these 2 lines. User management acquired the user lock. Order management acquired the order lock, but it never actually print the other line within the nested lock. In each thread, it doesn't do it. Why is that? Well, you can see that manage user is called within the main thread, and it takes 2 seconds, and manage order takes 1 second to complete. So when the start is called and when this manage user function is called, what happened was that each other acquired its own lock, right? So manage user acquired the user lock, and manage order function acquired the order lock. But when the manage order try to proceed to acquire the user lock, it knows that it's being blocked by the user management, right? Because it's still holding this. Whereas the user management is waiting for the order lock to be released in order to continue it. But at the same time, the order management is being blocked by the user management. Therefore, no one can release the lock and no one can continue. Okay, so in this type of scenario, when we have a hierarchy and we have complex resource sharing, we need to try our best to avoid having such a strategy of nested locks, because nested lock can potentially cause deadlocks. Okay, that's everything I want to cover in this video. If you have any questions, please let me know. If not, I will see you in the next one.